I was working with her.
Thank you for that.
I was working with her last night, and I need to work with her today in order to get her ready for the exam tomorrow morning at 9:30. So anyway, I don't think we'll be sitting through the whole 4 hours. So just wanted to let you know why I will disappear at one point.
Okay.
Good.
Not exactly a question, but I'll accept it.
Yeah.
I'll accept that.
I'll accept it. right.
Remind me what Z is.
Okay.
I'm going through my formulas.
Yes. Okay. So Z is complex impedance. And it is such that you have this thing called R, which is resistance. If you draw an XY plane, then you also have this thing called reactance. And then this is reactant. R is real, if you want to think of it that way. Resistance is the ability of something to resist the flow of DC current. Reactance is something that happens when an inductor or a capacitor starts to behave in a way. It's a measure of how reactive it is to AC at a particular frequency. So for an inductor, it's 2 pi times F times the value of L. That's XL. XC is a measure of how reactive a capacitor is to AC current. So by looking at this, if our frequency goes up, because it's the very same frequency for both, if our frequency goes up, then this tends to go to infinity. If our frequency goes down, the capacitor is 1 over something very big, which is 0. So this is for frequency of infinity. Well, okay, frequency of infinity is known as AC, right? It's in the extreme. And what did we do? What did we show yesterday? That if we have a capacitor, what happens if you put AC into it? It basically turns into a short circuit. A short circuit is 0 resistance. If we take an inductor and we do the same thing, we put AC into it, it basically turns into an open circuit. Open circuit is an infinite resistance. Now we're going to take it all the way at the other extreme. 0 frequency. What is 0 frequency another name for?
Silence.
Wave DC.
That's DC.
Oh, okay.
So if we have 0 for frequency, 2 pi times 0, what's our XL? 0. If we have 0 in the denominator for the capacitor, we have 1 divided by 0, which tends to infinity. And that's how we get our open circuit and closed circuit. That's how we get our open circuit and short circuit approximations for our capacitor and inductor. Basically, the X goes up and down. Resistance is resistance, but the X goes up and down. Now, because these properties are actually shown to be perpendicular on this graph, if I have an R, oops, didn't mean to do that, obviously. Change colors. If I have a resistance that, let's say, 300 ohms, and I have at a given frequency and selection of L and C, because resistance is not frequency dependent, but reactance is, what will happen is if I have this, a capacitor in series with an inductor, my reactance is add XC plus XL. And in fact, now what we have to do here is realize that in effect, the capacitor is actually negative, because we can't really, you can add reactances, but really you have to add their impedances. And their impedance, inductor goes this way, and the capacitor goes this way. So a capacitor is negative, inductor is positive. So this is minus 1 over 2 pi FC plus 2 pi FL. We can add those together, and the one goes up and the other one goes down, and it could be somewhere in here, or it could be 0. But either way, let's say it ends up right up here at the top. So we have an R and we have an X. This magnitude right here is Z. That's your complex impedance. So we could say that if we have a reactance of 300 ohms up, then our complex impedance would be 300 plus J 300 ohms. Where J is the up and down direction, or the imaginary term.
And the
And
J is joules.
no, J is
No.
the imaginary axis.
J
So,
is imaginary axis.
because you could have X and Y, or you could also, in engineering, we do I and J. You can also do I hat, J hat, X hat, Y hat. Those are just basically indications of those axes. We have to call them something.
Right.
And notice it's a little j, not a big J.
Right. Oh, yeah. Yeah. Okay.
Okay. So now we could also say, because we have a triangle that looks like this, where it's 300 and 300 like that, and it's a right triangle because they're perpendicular, by the Pythagorean theorem, this actually right here, this length is 300 square root of 2. So we can also say that our impedance is 300 square root of 2 times sine 45 degrees plus, or sorry, I got that. Cosine of 45 degrees plus J sine of 45 degrees. So this is just basically trig, and it's saying that this is another way of describing this point. But because our impedance Z is an actual thing, what it means is that if we do Ohm's law, well, we can rewrite Ohm's law in terms of impedance rather than resistance, and then it becomes E equals I times Z. And if we were to draw this here, we know that if our I is right here and our Z is up here, we multiply those together, we get the amplitude of the I and the amplitude of the Z. But we also have this cosine 45, J sine 45. Or we can say this is angle 45 in shorthand. What that means is that our E is I times magnitude of Z times angle 45 degrees, which means that our voltage is now 45 degrees further along as we spin the axis starting at 0. Our voltage is up here and our current is here. So as these things rotate around and around and around, the voltage gets there first, right? Because these things always are 45 degrees apart. So at some point, our voltage is like right over here because it's rotating, and our current is over here. As we're going around, the voltage is always leading the current.
Is that what they call forward power?
No,
Okay.
this is used in something called power factor. If you've ever dealt with
I've heard of that. Yeah.
if you've dealt with an electric motor, let's ask, what is an electric motor? What's it made of inside? It looks like that.
It's an inductor inside.
It's a giant inductor with windings in it. Okay, inductors are what? They're big coils, right? So if it's an inductor, which one of these, L or C, is it? An inductor is an L or a C?
Be it the L.
It'd be
It's
L.
the L.
That's right. Okay, so if it's L, does it have positive or negative? reactance. Which way does an inductor go? Inductor goes
Positive.
up. That's right. Which means that in a motor, what you end up with is you have some resistance, and this is your impedance, which means that in a motor, your voltage leads your current. And the cosine of this angle is the power factor of that particular device. The power factor is really important because only power that is in phase, only voltage and current. So I'm going to erase this. Okay, what's the other part of Ohm's law? How do you write it? P is equal to
I
I times E. Okay, but what if E is actually equal to IZ, which is equal to I magnitude of Z times an angle of 45 degrees? Well, so that means that our power has a factor of sine 45 degrees and a cosine of 45 degrees. And it looks like that. Only the part of it that's in phase actually makes real power in a motor. That would be this part. So if I have my current that's over here and my voltage is over here, and I multiply them together, what I get is I don't get this entire voltage. There's my voltage and current. I get this part of the voltage only, actually making real power to turn the motor. And this is the cosine of the angle. So it's real power is VI cosine of the theta, which is the angle between the two, which is a result of the impedance. This cosine theta is known as the power factor. And it's really important because, well, how much voltage and how much current is the power utility actually providing you? They still have to deliver them, right? I mean, they can't not provide them. Your motor's requiring it, but your motor is such that you're only actually using about 70% of it, which means that they have to size the current, they have to size the wires for all that current, even if you're not really using the power that it's making. Which is why if you have a motor that looks like this, where your power factor is like this. So here's one, and here's the other, and you have this big angle, you're maybe only using 50% of the power. How would you fix this? If an inductor makes a reactance that goes positive, what makes a reactance that goes this way?
You'd throw a capacitor in there.
The capacitor.
When you're building a factory, you often have a bank of capacitors that senses what your power factor is and puts a bunch of capacitors in series with it, so that it takes this and makes it so that these capacitors, even though they're not doing any work, they're making the utility happy and they're saving you money because the utility doesn't have to provide you lots and lots of current that you're not using. Pretty cool stuff, right?
Yep.
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 Very cool. Thank you.
Okay. All right, you guys ready? We're on to the general exam. Okay, now we're on to the general material. Now, let me ask, have people actually been reading through the general?
Some, yes.
Some? Okay. All right, so this material is what we're going to say similar, but more complicated than the technician license, but a lot of it is overlapping. So what we're going to do is share what I'm looking at on the screen right here. Okay, notice, what is reactance? Opposition of flow to AC. So that is the beginning of the general class book, right? We are now into that. You use ohms. Reactance is the flow of alternating, is something that opposes alternating current. And look at that, XL is 2 pi FL. XC is 1/2 pi FC. So we've already done that. That's also how you get, that's also how you develop something called resonance. If you pick a capacitor and an inductor and a frequency where they completely null each other out, then it makes a nice clean path for the current to flow, and it's frequency dependent, and you get a peak of your current, which is resonance. Okay, there's how a capacitor reacts. Okay. What happens when the impedance of an electrical load is equal to the output impedance of a power source, assuming both impedances are resistive? This is basically why we do impedance matching on our transmitter and our antenna. You can deliver maximum power because the signal doesn't bounce back. You can think of it as similar to standing wave ratio. If you give it a nice clean path, it keeps going out, you never see it again. If you never see it again, that means you delivered all the power to the load. A load in this case is an antenna. A load could also be a resistor. What is one reason to use an impedance matching transformer? We kind of covered this yesterday, but let's say that we have a speaker, and the speaker has an impedance of 32 ohms. And I have an output circuit, which is a transistor, and it goes through a bunch of other stuff. Here's a capacitor. And what would I use the capacitor for? What's a capacitor used for when there's AC and DC? What passes through a capacitor?
It blocks the DC.
It blocks the DC and lets the AC through. Exactly. Okay. So let's say that I have this circuit, which looks something like this. Here's another capacitor. Here's my transistor amplifier. And my output impedance, if I were to put a wall here and then look back at what my transistor amplifier has, my output impedance is, let's say, 2 ohms. Is that a good match? I have 32 ohms on this side and 2 ohms on the other side.
No.
No, if I try to put power out into my load, I will get power bounced back because it's a bad match. So what did we say yesterday, or no, whatever day it was? Here's a transformer. If I have a number of turns N1 and a number of turns N2, that allows me to get proportional voltage. So V1 and V2, they are proportional. So if I have 3 to 1 and I have 10 volts over here, I will get 3.3 volts over here. Because of conservation of energy, if I have 1 amp over here, I will have 3 amps over here. And if I have a load here, what ends up happening is if I take an equivalent resistance or impedance, V is equal to IR, P is equal to IE. Well, I'm calculating my resistance. R is equal to 10. And over here, R is equal to 1.1. Well, what's 10 divided by 1.1? Equal to 9.
9.
What's my ratio? 3 to 1. Which means that I have a ratio in turns of 3 to 1, and my resistance ratio, equivalent resistance, is 9 to 1. I get the square of the number of turns. So if I get the square of the number of turns in the ratio, and I have to convert 2 ohms to 32 ohms, what would I do? What's the ratio that I need? 32 to 2, which is 16.
16.
Which means what does my turns ratio have to be?
1 to
Remember-
16.
Nope. Remembering that the impedance goes up as the square of the number of turns.
4.
It would be 4. So my transformer would be 1 on this side and 4 on this side. So I'd have like 3 turns and 12 over here. And I'd have an impedance match. 1 to 4. Or in this case, 3 to 12. Because my ratio is 4. And that's what we use, that's how we use a transformer for impedance matching.
And that's what a balun is on the bottom of a dipole.
That's yes and no. A balun also tries to balance the currents between the two sides. But yes, it can also be used as an impedance match. You can have a 1-to-1 balance, which is 50 ohms to 50 ohms. You can have a 9-to-1 balun, which is 50 ohms and 450 ohms. So depending on how you wire it and the number of turns, that determines that forces the currents to be equal, and it changes the impedance match. It changes the impedance ratio.
So when you're using 300 ohm ladder line for your antenna,
Mhm.
how are you matching the ohms down? How are you bringing the ohms down to 50?
I have a balun.
Okay.
I have an impedance matching transformer in the tuner.
All right.
If you buy an antenna tuner that has a ladder line output, it will have usually a 4-to-1 transformer in the tuner. And 4-to-1 is pretty close. It'll get you to 200 ohms. Sometimes it'll be 6-to-1, but that'll get you 300 ohms. Or sorry, it'll be 4-to-1 impedance match, so 2-to-1 winding match.
All right.
And of course, you can buy a core, you can buy a ferrite core and wind these yourself, which is what's so cool about it. Okay, which of the following devices can be used for impedance matching at audio frequencies? A transformer, a pi network, or a length of transmission line? Yes, it's actually true. At radio frequencies, sorry, not audio frequencies.
Yeah.
So a length of transmission line. Okay, so here's an interesting thing. Let's say I have a 50 ohm load and I have an antenna that is, we'll say a 50 ohm feed point, and we'll have a 10 ohm load. Well, you want it to be matched, right? So I can take any length coax here, and then I can say that's 50 ohms. And then in right here, I can actually use a quarter wavelength of cable of some other impedance. So let's say that this is, I'm trying to do the quick math in my head here. If it's 10 ohms and it rotates, then that will cause it to be 1 over that. I'm trying to figure out what it's supposed to be. But let's say that it's, 200 ohms. It's not going to be exact. But basically that will actually cause this 10 ohm impedance to look like something else, which is kind of amazing. That because this is a quarter wavelength long, depending on the length of that matching section, that will actually change the overall impedance and make it something you can work with. And that's actually an impedance matching transformer. We use these kind of things for antenna systems where we have multiple antennas fed by the same signal. Let's say that we have 2 antennas that are in parallel. Let's say we have a vertical here and a vertical here. And a vertical has a feed point of about 36 ohms. And this one has an impedance of about 36 ohms. Well, what happens if we put them in parallel? What do we get? How many ohms? What's a 36 ohm resistor in parallel with 36 ohms? The formula for parallel resistance?
It would be half.
Yep, is R1 R2 over R1 plus R2. This works for impedances as well, which is 18 ohms. So our Z in is 18 ohms. Well, is that a good match? I
No,
don't think so. No, I don't think so. So what you really want to do is you want to make each of these so that you can feed power into it at 36 ohms. So you'd actually take each of these and run a matching transformer, which is just a piece of coax, to here, so that each of these appears at this point to be 100 ohms. Why would you do that? Because then you take these and you run them into a T. You feed power in, and what does your 50 ohm cable see?
50 ohms.
100 in parallel with 100, which is 50. So this is a quarter wave match. This is a quarter wave match. Magic, right? Kind of is. And when you get to your extra class exam, after you've killed your general exam, you'll learn about something called a Smith chart. And what I'm going to do is just pull up a picture of a Smith chart. This is a Smith chart. And I am not seeing it yet. There we go.
We're not seeing your eye.
There we go. This is a Smith chart. Notice this horrible looking thing. Well, in effect, see this right there in the center where you have 1.0 right there in the middle, where all the things seem to converge. So you have these curves, and notice you have angle of reflection coefficient in degrees, angle of transmission coefficient in degrees. And what this allows you to do is figure out how long of a piece of matching transmission line you need and what impedance it can be to do your work for you. So instead of having to do all your calculations, you grab a Smith chart and you start at a certain place and you draw lines on it, and you eventually get all the way to the center, because the center where it says 1.0 is exactly where you want to be. And you can basically go up and down and around. These are resistance and reactance axes. It's a really cool chart, and it simplifies the process a great deal, even though it looks pretty awful. So that's on the extra exam. So when you get ready for your extra exam, that will be covered on it. Okay, let's see, share screen. Okay. Which of the following describes one method of impedance matching between AC circuits? You can insert an LC network between the two circuits. So an inductor and a capacitor can change the overall impedance. And let's see. Okay, decibels. Does everybody get decibels? Are we good for decibels from yesterday or the day before or whatever that was? How about current division?
I'm
Yeah.
completely lost in all the math. I can't keep up with you. So I'm just going to gather what I can.
Well, if you're lost, then other people are probably lost too. What do you need?
I'm not going to go all the way back. I just can't keep track of it.
So, okay, which part? I mean, Ohm's law? You got Ohm's law.
No, I understand Ohm's law.
Okay.
But when you get into that other stuff and I can't keep track of where you're going at the time.
But which
I get
other
lost.
stuff? Which other stuff are we talking?
Okay, when you draw your diagrams, I never know where you're going to go to the next spot. And so then I lose track of you.
Okay. Are we talking?
And I
Yes,
think
sir.
it's because of my glasses, because I have to keep changing glasses.
Are we talking on like on a circle, or are
No,
we
no,
talking?
no. On your circuit boards, on your diagrams,
Okay.
I get lost and then I can't
All
keep
right.
track. I'll change my glasses and then I've already lost you.
Okay. Are you okay with the decibel?
Yeah,
Okay. So it's not really the math that's getting you. It's the diagram.
yeah. I
Okay.
can't keep track of it.
Okay.
And if
All
they
right.
give me one on my test Friday, well, of course, they'll give me time to change my glasses.
Yeah. Okay.
Yeah,
So
Scott,
yes.
my computer has a hard time seeing your yellow.
Yeah.
Yeah, mine
Okay.
too.
I'll
And
try
I'm
to avoid
thinking if
using
you
the
had-
yellow.
orange or something, it might be a little bit better, but there's times when I'm like, oh yeah, that's where he is.
Yeah,
Um,
yellow's not, or orange isn't one of the choices, so I'll
Yeah.
avoid using it. I'll avoid using yellow.
Yeah,
Okay,
thanks.
so how about as far as this how about as far as this current divider?
Okay, that right there is fine, but once you start drawing on it, I get lost.
Okay. So what we're gonna do is we're gonna draw this circuit. Okay, so there's a battery and here's a resistor.
Mm-hmm.
There's another resistor. This is R1 and R2. Our current flowing this way. We have current flowing this way and current flowing this way.
Yeah.
Okay. Important fact. Both of those resistors experience the exact same voltage. Would you agree with that?
Yes.
Okay,
'Cause
because they're in
parallel.
parallel. Okay, they experience the same voltage. Well, what happens when you get two different resistors? How are the currents going to split?
Based on the resistance.
Yep. So if these resistances are equal, the currents are going to be equal.
Equal. Yeah.
If you have one resistor that's 1 ohm and the other one that's 10 ohms, which way is most of the current going to go?
The 10
One,
ohms.
one ohm.
One
no,
ohm.
least
The
resistance.
least resistance.
Oh,
Going to
okay.
follow the least
Yep.
resistance. Well, you can actually figure out based on this, if I have E up at the top, and I can figure out that I1, because E is equal to, let's say, 10 volts. Well, this is 10 volts. I'm going to just look at the left-hand resistor. So I1 is equal to 10 divided by 1 is 10 amps. I2 is equal to 10 divided by 10, which is 1 amp. Now, here is the next thing that we're going to look at. If I have a total of 11 amps flowing, does everyone agree with that?
Mhm.
Yes.
Okay. And I am the battery and I don't know what all this stuff is. All I know is that there's 11 amps flowing. Could I figure out what my equivalent resistance that I'm seeing behind the wall is?
Yes.
Yeah.
Sure. I
Using the
use Ohm's
formula.
law again, right? R is equal to E over I, which is equal to 10 over 11, which is 0.9 ohms. So that parallel combination has a value of 0.9 ohms. If I couldn't see what was behind there, I would still know that it has an equivalent resistance of 0.9 ohms. That's actually important. That's an equivalent resistance. If I were to go through and figure all this out and do the derivation, I would also find that R total is equal to R1, R2 over R1 plus R2. And we can see that this is actually 1 times 10 over 1 plus 10, which is 10 over 11, which is 0.9. Look at that. We get the same answer. This is your equivalent resistance for a combination. If I have 3 of them, it would be R1, R2, R3 divided by R1 plus R2 plus R3.
They're multiplying on the top and adding on the bottom.
Multiplying on the top and adding on the bottom. Okay,
This current
impedances.
that's flowing through the diagram, is
Mhm.
that self-sorting? It's not being assigned by a switch to you go this line, you go to
Nope.
the right line?
Nope. It just
It's
it
like
just follows the
cattle
path of
feed.
least resistance. So impedances Z are treated the exact same way as resistance. And inductances are treated the exact same way as resistances. You calculate them the same way. But something that's important to note, let's say that I have a capacitor in parallel with another capacitor. What is a capacitor? I mean, what is physically a capacitor?
It's two plates.
2 plates in parallel, right? Okay, let's say I draw one there and I draw another one right next to it, they're almost touching, because effectively they are touching, right? What does that look like to you? a bigger
Capacitor.
capacitor. Capacitors in parallel add like resistors in series. When you're doing the capacitor, capacitors in parallel add. So what if I do one and then the other? Capacitors in series are calculated like resistors in parallel. This is the only reason, this is the only exception to the rule of adding in series and doing the parallel calculation in parallel. And this is why, if you look at how a capacitor works, it doesn't split anything because a capacitor charges up. Two of them in parallel just make a bigger one. This is something that you can just, say, oh, I can go back to that and understand why. Okay, let's see. Here's RMS. Okay, what is the definition of an RMS voltage? Does anybody remember what this is?
It's 0.707 of
Yes,
the
but what
peak.
is the actual meaning of RMS?
Root mean square.
But what's the actual meaning?
It's
Because this is what's
average.
important. Well,
Well,
It's the actual
so-
power.
yeah.
it's
Was
the,
it 70% of this is useful and the other 30% drops
oh
off?
no, it's all there. Root mean RMS voltage is the equivalent DC voltage that generates the same power as whatever wave you're looking at. So if I have a sine wave, a DC voltage that would generate the exact same amount of power would be 0.707 times the peak. Now, again, if we were to look at a voltage, and I don't remember if this was after or not yesterday. So here's volts peak and minus volts peak. The average, the DC voltage that would generate the exact same amount of power has a value for a sine wave of 0.707 times the peak voltage. If I were to take this and make this a square wave with plus and minus volts peak, when we're in this section, we are always producing full power all the way on the left. Does everybody agree?
Yes.
Because power is equal to voltage squared divided by the resistance. When we're down at the bottom, what is minus VP squared? It's VP squared. The minus goes away. So it does not matter if it's plus or minus. It's just how far positive or negative it is. So what is the equivalent DC voltage that would make the same amount of power as the red line?
It's the same.
It would be right there. So in this case, VRMS is equal to the peak voltage. Because it goes back to the definition of the RMS voltage. And that's why it's important to remember what the real meaning of RMS is.
Root
It's-
mean square.
It's the equivalent DC voltage that makes the same amount of power as whatever you're seeing. So if I were to draw a voltage waveform that looked like this. Or, I mean, how much power would that make?
Not much.
Not much, yeah. How about if I drew one that looked like this? How about that?
You can't have that much gap between the ups
Sure you
and the
can.
downs.
You
Okay, yeah.
absolutely can. How much power would that make? Do you think? It's off a lot of the time, right?
That looks pretty wimpy.
It is pretty wimpy. Yeah, your RMS voltage might be about here. If even that much, it might be lower. Your RMS voltage might be here. It might be, 0.2 times volts peak. Because that
So this-
waveform, you can have a high voltage, but if it's not there for most of the time, it hardly does any work.
One way I found to think of this
Hmm.
is if the waveforms are icicles,
Okay,
and to get the RMS, you melt them.
okay, because that's integration. That's close. Yeah, I mean, it's a square time
It's a
average. mean. Yeah,
visualization tool.
yeah. Okay, so what is the RMS voltage of a sine wave with 17 volts peak? Okay, so we're gonna draw our sine wave. Man, I'm having trouble drawing straight lines today. There we go. Plus 17 and minus 17. What is our formula for RMS? For a sine wave?
0.7. Well,
V peak times 0.707, which is 17 times 0.707 is 12 volts RMS or 12 volts DC. Because that's really what RMS is. In other words, a 12 volt DC voltage will make the same amount of power. Okay. Let's go back to the book. Okay, what is the peak to peak voltage of, oh, here we go, an RMS voltage of 120 volts. What is 120 volts? Where do we find that?
AC.
Wall socket.
Wall socket. Okay, we have 120 volts. It's volts RMS. Okay, so by the formula, V peak is equal to V RMS 0.707, like that. So we have 120, and we divide it around, and we find that volts peak is equal to about 170 volts. Which is why, if we put it on an oscilloscope, we would actually see this. We'd have plus 170-ish and minus 170. Make sense to everyone?
Mhm.
Good. That's a fundamental thing, RMS voltage. Because it comes into play lots of other places too. Okay. How many watts of electrical power are used if 400 volts are supplied to an 800 ohm load? Okay, well, power calculations, we can take it as a one step or a two step. Well, 2 parts of Ohm's law, P is equal to I times R. E is equal to, sorry, P is equal to I times E. E is equal to I times R. So if we rearrange this one, we can say that I is equal to E divided by R, and we can substitute the I right there. And we can get E divided by R times E is equal to E squared over R. So the formula, the question said, if we have a 400 volt power supply and an 800 ohm load, well, we get 400 squared divided by 800 is equal to 400 divided by 2 is equal to 200 watts. I believe that was the answer for it. So what's nice is you can always go back and rederive the equations if you forgot them. Okay, here's another one. What would be the RMS voltage across a 50 ohm dummy load? A dummy load is a resistor, purely resistive, dissipating 1200 watts. Okay. Well, let's do the calculation. 1200 watts, 50 ohms. Okay. P is equal to I times E. E is equal to I times R. Everyone agree with that?
Yeah.
We have our power, we have our resistance. So we can rearrange this again, these two, and we can get P is equal to V squared divided by R. And we have 1200 is equal to V squared divided by 50. V squared is equal to 60,000. So V is equal to 245 volts RMS. Okay, so here's the next question. If this were being made by a sine wave, what would the peak voltage be? Somebody tell me the formula. VRMS is equal to. Come on, somebody tell me. VP
divided-
times 0.707. Everyone agree with that?
Yes.
Okay, so 245 is equal to V peak times 0.707. And I got to grab the calculator for this. 245 divided by 0.707. And I get V peak is equal to 346 volts. So now if I were to draw this, I would get a V peak of 346. What would my negative peak be?
Same.
Negative
Minus
346. So what would my peak to peak voltage be? This is called VPP.
It would be double that.
Double that,
690
so
something.
692.
Yeah.
So it's important to note when you're given a number, whether it's volts peak, which is measured from 0, or volts peak to peak. PP is peak to peak.
Scott, real quick, is there any specific reason that you changed the E to V in your formula?
Oh, no.
I mean, I
Force of-
know
for-
E and
Force
V-
of habit.
Okay, I mean, I know it's interchangeable because I've seen that in my studying. I didn't know if it was just because then
There we
it
go.
went to VPs.
Yep. Well, right. And for the formula, E is equal to I times R, but then you measure volts RMS and volts peak. So that's, yeah.
Right, which is fine.
Yep.
If that was the thought process, that's great. I was just
Yeah.
trying to,
No, I made a
follow.
little jump there.
no, that's fine. I just wanted to make sure I was following the thought process.
Yep. Stream of consciousness. Sorry about that.
Nope, it's
Um,
good.
Okay, what is the ratio of peak envelope power to average power for an unmodulated carrier? Okay, so this is getting into a little bit different thing. So peak envelope power is, there's something called a modulating envelope. So here's a carrier. It's always the same frequency, and the carrier is at a typically much higher frequency than the modulating frequency. So this is usually like, let's say, a megahertz. And the modulating frequency would be voice, which might go like this. Much slower. But what this will do is this will shape that waveform. So the carrier will look like this. And now I can erase this. And look what we have. We have a carrier that's being now shaped by another waveform. What is this called? This has a name.
Modulation.
What kind of modulation?
Amplitude modulation.
That
Amplitude.
is AM. That's amplitude modulation. So we have now modulated a carrier frequency, which is on the inside, with an envelope. by
All of
basically
the,
shaping it.
all the waves we've seen up till now have been equidistant above and below the x-axis.
Mhm.
And now you've shaped this one to look like a fish.
Yeah,
Why
but
is it not moving up and down
is.
equidistant from the axis?
It is. Here's the axis. There's a central axis.
Okay. How does it get, why does it get shaped and how does it get shaped?
Well, if I multiply my voice times a carrier frequency, something like using a mixer, they're two different frequencies. And that's essentially what we do for AM. We use a mixer to mix a voice frequency with
So this
a
is a
carrier
picture
frequency.
of that product.
Yep,
when
this
they're
is what
mixed-
AM actually looks like.
They're mixed thick and
Yep.
then they're mixed thin toward the tail of the fish.
Well, when you say mixed thin, I mean, this picture that I drew, which looks like this, in time, that is your voice. That is the waveform of what your voice looks like for a little period of time. If I were to make another picture of your voice that looked like this, and I put a carrier in it, this is over a longer period of time, it would basically just fill it. You'd never actually be able to see the waves. You'd never be able to see the carrier frequency. It would look like that. And that is what your AM would look like. It would be shaped by your voice.
Okay.
Okay, so if we have an unmodulated carrier, that means it's just always the same amplitude. So the ratio of peak envelope power to average power would be 1. This is just something to remember. Okay, but notice when transmitting a single sideband signal, the amplitude will vary with time, AM as well. The average power might be considerably less because at some time, that thing shrinks way down. So the ratio of peak envelope power to average power. What is the peak? The peak is the biggest point. If it's unmodulated, we're always big. So where in this waveform where does my peak occur if I have points A, B, and C? Where does A,
Stop.
right? So that would be the point at which my peak envelope power occurs.
Is there also a negative version of that on the bottom of the
Well,
way?
here, yeah, well, right. But remember, power doesn't matter if it's plus or minus. So let's say it looked like
Oh.
that. Well, because you always square the voltage, right? If you square the voltage, the sign goes away.
Negative goes away.
Right. So this would generate what the PEP is, the peak envelope power. The average power is how much energy this makes over time, which is why if you, let's say, take your microphone and go, let me make sure that I have music on. What is that sound?
Sounds like a constant.
That sounds like a constant, right? Constant amplitude. And that is a constant tone versus speech. Which one do you think is going to really see how much power you're going to put out at a peak?
The constant.
The constant. That's why some people will whistle into their microphone to see how much power they're actually going to put out when they peak. Because if you speak into it, it's going to vary a great deal because your voice varies a great deal. Okay, what is the output PEP of an unmodulated carrier if an average reading watt meter is connected that measures 1060 watts? If it's unmodulated,
Yeah.
that means it's just a
1060.
carrier, you'll get the exact same amount. Okay, so these two questions, we had a nice discussion about this yesterday after class. So my apologies if you weren't around for that, but we're going to cover this right now because this raised a couple of questions. So the question is, what is the output PEP of a transmitter if an oscilloscope measures 200 volts peak to peak across a 50 ohm dummy load? Okay. Now, what was that voltage given in? 200 volts peak to peak. What does volts peak to peak mean?
It's all the way up and all the way down.
So what is our actual peak voltage?
400 volt.
100 volts.
100.
Okay. So it's 100 and minus 100. Agreed? Okay.
Okay.
So that's our VP. So what is our RMS voltage here? VRMS is equal to VP times 0.707. That would be 100 times 0.707 is equal to roughly 71 volts. Or 70.7 volts. Okay, if I have 71 volts and I have a 50 ohm load, what is my power?
Or is IE?
Right? I could also just make that jump to E squared over R, because P is equal to I times E, and E is equal to I times R, and I do a substitution, and I get P is equal to E squared over R. And because this is already RMS, that is useful for power calculations, right? Because that's an equivalent voltage that makes a certain amount of power as the original waveform, right? So it's 71 squared divided by 50, which is roughly 5,000 divided by 50, which is 100 watts. Does that make sense?
Yes.
Good. Okay. Because we were talking about that in quite a good amount of detail yesterday after class. There's another one, which you can do the same thing. The output PEP from a transmitter of an oscilloscope measures 500 volts peak to peak across a 50 ohm resistive load. It's just basically the same calculation, but with different numbers. Okay, let's see. Everybody should know this. What dB change represents a factor of 2?
3.
3 dB. It's almost 3. It's about 3. It's 3.0 something. But that's not bad. Okay, now this is another interesting one to know. If you have a 1 dB loss, that is about 20.6%. So if I have 1 dB of loss, 20% of my power goes away. Okay, resistors and capacitors in series and parallel. Okay, resistors in series do what, everybody? Add. Inductors in series do what?
They too add.
They also add. Resistors in parallel, what do?
Divide the current.
They divide the current, so the resistance gets smaller. Inductors in parallel do what? They also divide.
It's resistor.
They also divide. They act the same as resistors. So what's the outlier? What's the weird one here?
Capacitor.
Capacitors behave the opposite way. So 2 capacitors in parallel will add. 2 capacitors in series will divide. Okay, let's see. Here's a little bit of use of pico and nano. These are with regard to units. Does everybody remember your units? Mega means, what does mega mean?
Million.
Million. Okay. How about micro?
1 million.
1 millionth.
Micro is 10 to the 1.
10 to the minus 6, which is 1 millionth. And this is a million. Okay. How about a nano?
10 to the minus 9.
10 to the minus 9, which is 1 over a billion. And pico?
10 to the minus 12.
Yep, which is 1 over a trillion, or a trillionth. Now, why are these really important? Micro and nano and pico?
Correct.
Because capacitors and inductors are they have, actually milli is important for inductors too, but those are typically fractions, because a Henry is a really big unit of inductance, and a farad is an enormous unit of capacitance. So we often end up using we use milli and micro and nano and pico for these things. So For capacitors and inductors, we end up using these units in front of them. So 1 microfarad is 1/1,000,000th of a farad. That's actually a fairly big capacitor. 10 picofarads is 10 trillionths of a farad. And we use these all the time, like a 10 or a 22 picofarad. We also use, for inductors, we say 3.3 millihenries. We use these things for reactors on motors and stuff like that. Okay, moving on. Get back to here. Share. Okay. What is the equivalent capacitance of 2 nanofarad capacitors and 1 750 picofarad capacitor connected in parallel? If you have a question, you just draw it. So we're going to draw it. In parallel. What happens if capacitors are in parallel? Capacitors
They
in
do.
parallel just
They
make
add.
they add. They just make a bigger set of plates. So we have the value, which is oops, I lost my place. They have 5 nanofarads and 5 nanofarads and a 5 and a 0.75. Add them together, you get 10.75 nanofarads. Now, let me ask this. Let's say that I have 10 picofarads and 10 picofarads and 10 picofarads. What do I get?
30 pico.
You get 30 picofarads. Okay. What if I have in this a 0.001 microfarad?
It's going to be about 0.001 microfarads.
Yeah, because what is a microfarad? That's a millionth. And these guys are a trillionth. So 0.001 microfarads is actually considerably bigger than 10 picofarads. So you have to be careful when you're looking at the units. The units are really important.
Scott, do you find it easier to convert to the largest unit or the smallest unit?
Yeah, I don't think it matters. Whichever way makes you more comfortable. I don't like working with decimal points, so, you know. What causes a voltage to appear on one side of a transformer when a voltage is put on the other side? Remember how a transformer is actually built? It's a core with wire wrapped around it, and then another wire is wrapped around the other side of the core. This core constrains the magnetic field inside it, which means that the magnetic field that's generated on one side will appear on the other side. A current generates a magnetic field. Magnetic field generates a current. It generates a current. So if I have a current flowing over here, I end up with a current flowing over here. This is known as mutual inductance. Okay. If I have a transformer and I take it and I go like this and I have a 10 to 1 matching, or 10 to 1 ratio, and I have 100 volts over here, and it's got to be AC, what am I going to get over here?
10 volts.
10 volts. Okay. Now, what if I take this and I have a 10 to 1 transformer and I put 120 volts AC over here? What am I going to get on the other side?
1200.
1200. Okay, so let me ask this question. Let's say that our turns ratio is instead a stellar 100 to 1. and I have 12,000 volts over here. What am I going to get on the other side?
120.
120. Okay. How about if I take this away and I put the same ratio, 100 to 1, and I put 120 volts in over here? What am I going to get on the other side?
12,000.
12,000. I can operate it in both directions. Okay. This is why if you have a power outage, you should never hook up your generator to your house wiring, because if you are generating 120 volts, you are backfeeding the power system. And what if this is a power line that is hanging on the ground somewhere? Or let's say somebody is working on that power line and assumes that the power's off. What will happen to the worker?
Fry them.
You'll kill the worker. That's right. And
So that's why they told me when I'm plugging in my generator, I need to break the circuit breaker
yep,
for the whole house.
yep.
So I'm just running my own little circuit in my house and not screwing with the outside world. And
That's why
hurting
we
it.
have disconnect
Exactly.
transfer switches.
Yeah, I got a transfer switch on the boat.
Yep. Because you could be on shore power, but you don't want to backfeed the outside system.
I have the inverter. And
Yep. Okay. Everybody ready for a 5-minute break?
Yes.
Yep.
Okay. I'll see you all in 5 minutes. All right. I'm back. Can I hear myself? Echo, echo, echo. Hello. It works.
I didn't go anywhere. I'm still here.
No, okay.
Bye.
All right. So does this stuff make any sense?
It does, but the math just gives me a headache.
Yep. Well, yeah, but the math is the language that allows you to describe everything.
Right. No, I
So-
understand. I get it. I get it.
And it really comes down to, you can study by not, you can study without it, but I think
yeah,
it helps.
well, like some of the discussion yesterday, some of it, yeah, like the decimal part, that to me is easy to remember, the 3 and the 10.
Mhm.
But some of it, it's a little easier to just try and memorize the answer.
Right. Well, I mean, if you can write this formula, dB is equal to 10 log base 10 of P2 over P1.
Mm-hmm.
That's the formula for decibels.
Right.
I mean, if you can memorize that, you can have your calculator do stuff.
Right.
So, but and that's the hardest part, I think, memorizing the formula.
Right. Right. Well, and that's the thing. There's a few of them.
Yeah.
There's a few formulas. So.
Okay, so we're going into transformers. So let's do transformers. More than meets the eye.
More
Anyone-
than meets the eye.
Anyone get that? You have to be a certain
Absolutely.
age. Got to be a
Every
certain
time you
age.
say Transformers, I think about Optimus Prime. and-
Optimus Prime. Yes.
No.
Okay, so let us draw this transformer. And we have a 4-to-1 step down. So let's say we have 120 volts AC. What are we going to have on the other side? How many volts?
30.
30 volts. Yep. It's proportional. Okay. But now, if we have, let's say we have a current flowing of 5 amps into this, how much current are we going to have on the other side? 20 amps.
20.
Because we're going to have the same amount of power on both sides. Which one needs bigger wire?
The 20 amp side.
The 20 amp side. So we usually call this the primary. And they call this the secondary.
Why
So-
does that number get bigger going from left to right, where the top number gets smaller going from left to right?
Because the voltage ratio is determined by the turns. Agreed?
Yeah,
Okay, what do we know about power and energy? Can neither be.
Created
or destroyed.
Okay, so what's the power on this side? Is equal to I times E. 120 times, 5 times 120 is 600 watts. 600 watts. Okay, if we have 600 watts over here and we don't know what this is going to be, equals 30 times I, current is 20 amps because our power has to be conserved. If it's not coming out as heat, if we have an efficient transformer, power in has to be the same as power out. Therefore, we have 20 amps on this side, on the secondary side. And if we have 20 amps on the secondary side, that wire better be able to handle 20 amps. This is exactly why if we're doing a power transmission system, let's say we have 1 million volts AC, and we have a step-down transformer, which connects to another transformer, which is another step-down transformer, and we have a turns ratio of 100 to 1. If we have 1 million volts on the left-hand side, what do we have over here?
10,000.
10,000. And we have 10,000 volts over here, and we have, let's say, 100 to 1 again. What do we have on the other side? 100 volts.
Okay.
Okay?
Yep.
So now here's the question. If somebody is using 100 volts at 20 amps, how much power are they using? Well, 20 times 100 is 2,000 watts. How much current has to be flowing here? P is equal to I times E is equal to still 2,000 watts. except our current is used at 10,000 volts. So our current is only 0.2 amps. Over here, our current is 0.002 amps. What is the formula for voltage with regard to resistance? E is equal to I times R. Everyone agree there?
Yes.
So if I have a resistance in my wire, but my current is only 2 thousandths of an amp because I'm doing it at 1,000 volts, and my resistance is, let's say, 1 ohm times 0.002 amps, what's my voltage drop? 0.002 volts. And now I can go through and say P is equal to I times E and figure out how much power I'm losing in my line. And that is 0.002 times 0.002. It's 0.00004 watts. That is my that is my power loss. So that also means that all I need for this particular case is something that's able to handle 2 thousandths of an amp because I'm doing it at 1,000,000 volts. This is how power systems work. That's why power transmission lines often operate at 765,000 volts. You generate a massive voltage, which means you get a lot of power by not delivering a lot of current. And then you transform it at local locations. That's how power systems are built.
So one question. So the first one you did, the 4-to-1, one step down.
Yep.
It was 120 to 30 and then 20 to 5. To me, had a little bit of a moment of clarity. I thought it looked like it was 4-to-1 and then 1 to 4 was
correct. Correct.
Right, the other way.
Right. Correct. And it's 1 to 4. The ratio is 1 to 4. And because you have to conserve power, if your voltage goes down, your current goes up.
Up, right, gotcha. So did that more complex one work, excuse me, the same way from 10,000 to 100? It's the same thing. It's the inverse going the other way.
Yep.
Okay.
That's why that is done.
The bigger number scared me. That's all.
That's why we transmit power at ridiculously high voltages.
Got you.
Because you don't have to deliver a lot of current. And because you don't deliver a lot of current, you have very little in the way of resistive losses in your wires. And since the power company is responsible for delivering power to you, the less power they burn up as heat in the power lines, the less their lines come apart, the less their lines sag in the heat, the less they spark and cause fires, and the more power they can sell. Right? Which is a good thing.
Yeah.
Okay. Let's see. Next one. Where were we? We are on turns ratio. And actually, they have a question about resistance. And will you look at that? An impedance match. The turns ratio of a transformer used to match an audio amplifier having 600 ohm output to a speaker having 4 ohm impedance. Okay, what do we know about an impedance match? If the voltage goes up, then the current goes down and vice versa by the same amount. So the impedance, the equivalent impedance, changes by the square of the turns, right? We sort of covered that already. So if you need a ratio of an impedance ratio of 600 ohms to 4 ohms, what would that ratio be?
150 to 1.
150 to 1. Okay. And what is the square root of 150? That would be about 12.2. So if you have a turns ratio of 12.2 to 1, or depending on which way you're going, 1 to 12.2. Now, how do you get 0.2?
A little bitty wire twisted sideways.
Yeah, or you could actually do it 10 to 122. You could do that because what's important? The overall number of turns or the ratio?
Ratio's king.
Ratio is the most important thing. There you go. Okay, so we're into circuit components, things that we haven't covered. Why would you not use a wire wound resistor in an RF circuit? We sort of covered this yesterday when we were talking about dummy loads. A wire wound resistor. What is a winding of wire called? It has another name.
A coil.
A coil. A coil is an inductor, and an inductor has impedance, right? So if we start looking at that again, we have a resistor. Let's say it's 50 ohms. Well, here's our reactance axis, up and down. And what's the formula for impedance or reactance of an inductor? It's 2 pi f-L. Well, the L's not going to change, but as we change our frequency, what happens to our reactance? At low frequencies, it might be here. At high frequency, it might be here. At really high frequency, it might be here. And we have to finish our triangle. Some places it might be here. And some places it might be here. So here's Z1 and Z2 and Z3. And the problem is that all of those are the same component, just acting at a different frequency. Try to use that. It doesn't work very well. That's why we don't do that. Unpredictability. Okay, a ceramic capacitor. That's basically two plates that are dipped in a ceramic material. They're really cheap. They're relatively close tolerance-wise, and they're really, really cheap. An electrolytic capacitor is, so a ceramic disc capacitor might look like this. Here's one plate, and here's another plate, and the whole thing is dipped in a ceramic material and two leads coming out of it. That's what a ceramic capacitor looks like. You can make them really cheap. They work great, but they don't have that high of a value of capacitance. Capacitance is defined by the size of the plates and the spacing between the plates. If I were to draw something called an electrolytic capacitor, that is actually two plates that are separated by a dielectric, but the dielectric actually has a tendency to have ions in it. So it doesn't allow flow, but it has a higher dielectric constant. Unfortunately, it's also such that you get pluses and minuses. So if I hook this up to pluses, everything is fine. If I hook this up to minuses, everything is fine. And actually it will work great because of the stuff that's inside it. It has a really high value of capacitance. Unfortunately, if you take this and you hook up this thing so that the minuses are over here and the pluses are over here, what will happen to your capacitor? You'll hear a zzz, and then you'll see a puff of smoke. And if you are lucky, these are actually built with a little set of score lines on top. They have a plus terminal and a minus terminal. And if you hooked it up backwards, what you will get is the stuff inside will boil because of all the current, and you will get these score lines opening up, and you will have electrolytic goo flying out of your capacitor, often with the sound of a gunshot inside your equipment. And then you have to clean it, and then you also have to replace the capacitor. So electrolytic capacitors are great because they have very, very high capacitance values. They're not so great because if you hook it up backwards, you fry everything and you let all this goop out of it. So if you're going to use an electrolytic capacitor, what's the rule of thumb? Everybody?
Make sure properly. Be ready for the goo?
Yeah, make sure that you follow the polarity. That's right. Okay.
Do they have longevity issues?
Nah, like anything. Yeah, but not really. I mean, they don't fail any more than anything else. So, polarized capacitors, incorrect polarity can cause it to short circuit. Reverse voltages can destroy the dielectric layer, and the capacitor could overheat and explode. Okay. What is the advantage of using a ferrite core toroidal inductor? And again, we talked about ferrites yesterday. That's one of the pages that I sent you guys in the recap of yesterday. Large value of inductance, magnetic properties of the core can be optimized, and most of the magnetic field is in the core. So that's basically how we build something called a balun. We take a ferrite core and we wrap wire around it. You use two different ones, and you get, let's say, one that is optimized for the high frequency band, one that's optimized for the very high frequency band, and so on and so forth. What determines the performance of a ferrite core at different frequencies? That is known as the mix of ferrites. That's one of the things that I sent you guys yesterday. A ferrite bead is basically a ferrite that is wrapped around a piece of wire. It creates an impedance in the current's path by providing a place for the magnetic field to sort of like spin around and die as heat. Okay, an inductor, believe it or not, has a little capacitance. Why does an inductor have capacitance? I'm going to draw an inductor and you tell me why it has capacitance. Take a look at it and tell me why it actually has some capacitance.
Does that have to do with making a current as it goes through the wires?
Nope. To give you a reminder, here's what a capacitor looks like. Can you see anything in here?
Space between the wires.
Space between the wires.
Oh.
You have voltages and spaces between the wires, so an inductor actually has a little bit of capacitance. Well, because of that, if an inductor has a value L, 2 pi FL, and let's see, J 2 pi FL, and C minus J over 2 pi FC, true or false? There is a self-resonant point at which an inductor will just resonate by itself. If it has both of those, an L and a C, it's the same thing as being this. Everybody agree with that?
Yeah.
And what is this thing right here? An inductor in series with a capacitor is a resonant circuit. So even though the capacitor is very, very, very small, it is not zero. So an inductor will have a self-resonant point. And if operated above that frequency, it will actually turn capacitive. The capacitance will actually become more important than the inductance will. Okay, the approximate, here we go, approximate junction threshold of a silicon diode. We talked about this, 0.7 volts. A germanium diode, 0.3 volts.
0.3.
Okay, what describes the construction of a MOSFET? MOS just means metal oxide substrate. The key here is FET. If you draw a FET transistor, what does it have? It looks like this. The gate, and here's the drain and the source. That makes the channel. So this is a capacitor essentially. So there's a thin insulating layer between the gate and the rest of the circuit. Okay, we talked about this as well. One of the stable operating points for a bipolar junction transistor used as a switch. A transistor function looks like that. So we have the linear region, which is the active region, and we have the cutoff down here and the saturation region. If we're using it as a switch, we do not want to use the active region because we don't want to know that something is halfway in between. We either want to know that it's off or it's on. So if we're using it as a switch, we use the saturation and cutoff regions of the transistor curve. Okay, now we're into vacuum tubes. Who knew we were going to be doing vacuum tubes? Okay, so we're going to draw a vacuum tube. This is a vacuum tube. What is inside a vacuum tube?
A
What is the-
vacuum,
A
nothing.
vacuum. That's right. What is a vacuum? It's the absence
Presence of
of
nothing.
stuff. That's right. It's the absence of stuff. Okay. So this is a vacuum tube. This is the anode, cathode. And this is a grid. So how many elements would you say are connected in this thing? How many things do you see?
3.
3. This is known as a triode. Okay, if I had another grid right here, how many elements would you see?
4.
4. That's called a tetrode. And you can have pentodes and stuff like that by adding additional control grids or screen grids. So what we're going to do is get rid of the second grid. We're going to just look at a triode. And the way that this works is that electrons are made down here at the bottom. And they want to float up to the top, which is positively charged. So normally, if you have the grid turned completely off, what will happen is that you'll have a drift of electrons through the vacuum. They will jump the gap from the cathode to the anode. So what is a way to block that from happening? What if you made the grid kind of negative? Would there be a tendency for these electrons to reach the other side, or would they be repelled by the grid?
It'd be repelled.
They'd be repelled. So by modifying the amount of voltage on the grid, what we can do is modify the amount of current, because what is current again? What is the definition of current?
The flow of electrons.
Flow of electrons. By modifying the grid voltage, we can modify the flow of electrons. That is what a vacuum tube does. It is very similar to a transistor, except that, what are we dealing with here? A vacuum. A vacuum. They both deal with current.
Electron flow.
Electrons. So how do you make electrons down here? Well, you can do this. Sometimes the metal, in order to get it to work right, it needs one of these. And this is actually a heater. So if you see a tube that glows in the dark, it's because the heater is turned on. It actually physically heats up the cathode and makes it start to have electrons that are flying around and floating off of it.
What physically is a grid?
A grid is literally, if you want to think of it, it can be, because a lot of tubes are circular, it can look like this. It can have a bunch of holes in it. I mean, it literally looks like a grid. It could also be something that looks like this. It can be literally a grid shape. It could be. They can take a lot of different forms.
In reading about vacuum tubes, I've seen the terms screen and plate.
Well, this is the plate.
The grid is the plate.
No, the anode is the plate. No, is that right?
Yes.
Yeah, anode is the plate. And this can be either a control grid or a screen grid. If you have multiple, you might have a control grid and a screen grid. So let's go back to the book here. And now that we know basically what a tube looks like, what element of a triode vacuum tube is used to regulate the flow of electrons between cathode and plate?
Grid.
Control grid. The primary purpose of a screen grid would be like a second grid. And that's to reduce the capacitance between the grid and the plate. Okay, that's about it for vacuum tubes for now. Nickel cadmium batteries. We still use NiCads. One of the best parts about a NiCad is that it can have a really high discharge current. And for a car battery, 12-volt lead acid battery, once it's down at 10.5 volts, you need to recharge it. That's at the end of its life. Okay, now we're into integrated circuits. An integrated circuit op-amp. An op-amp is an idealized amplifier that looks like this. It has a plus and a minus. And so it has a pair of inputs that are differential, and then it has an output. And again, this is an idealized amplifier. And when you put a differential voltage between the two pins, you get an output. So that's known as an op-amp. And typically, when you get an op-amp, you're not going to build one. You actually will buy an op-amp, and it's a very high gain amplifier on a chip, and it's an analog amplifier. Okay, an MMIC is a monolithic microwave integrated circuit. You just have to memorize that. CMOS is CMOS, complementary metal oxide substrate. This is a type of transistor chip. The nice thing about a CMOS chip versus TTL. TTL is transistor logic. Well, CMOS, MOS, you may recognize that from MOSFET. So a CMOS chip usually uses FET transistors, whereas TTL uses bipolar junction transistors. The big advantage of a FET is that it has that insulation between the gate and the channel. And by doing that, you have much lower current usage. So lower current means low power. So as a result, CMOS is often used for doing things like running your cell phone. TTL can be faster, but it uses a lot more power, makes a lot more heat.
You're using the term substrate for the S. Is that also the semiconductor?
The substrate is how the whole thing is built. So it's if you were actually to look at how a chip is made, you basically will make like a million chips on a layer of material. That layer of material is the substrate. So you basically build things on top of it and then cut that out from the big wafer. So they're made in enormous volumes. You can also have it so that a wafer could contain 1 billion transistors that are built onto the substrate. It's really an amazing thing. Essentially, the metal oxide substrate is the base for everything that's being built.
I asked that because I've seen the abbreviation MOS defined as metal oxide semiconductor.
Well, now I'm going to check. Complementary metal oxide semiconductor. Okay. Well, I learned it as a substrate, but I guess it could be a semiconductor. So, devices are built onto a P-type substrate. Okay, I'm gonna have to, after all these years, remember something new.
I can't believe I taught you something.
I know. Well, no, that's good, because that's how I learned it. So it's entirely possible that somebody who taught me wrong long ago. So complementary metal oxide semiconductor. See, I have benefit for being here. Thank you very much, Stephen. Or thank you very much, Stephanus.
Steve is good.
Steve, okay. Read-only memory is a ROM. Non-volatile means that when you power it down, it doesn't disappear. So good thing. Our phone, when we power it down, it still remembers what it is. You don't have to reprogram it. An LED is a diode that is forward biased, which means that it is carrying current in the forward direction. And instead of just turning on, it emits light. A liquid crystal display. Okay, so an LCD is actually a lot cooler than you think, because an LCD is a device that has a quarter wavelength of material in it. Light comes down into the material. When this light here, when the LCD is powered on, what it does is it causes this light to become polarized. Well, by virtue of this quarter wavelength, it actually causes the polarization to rotate, so that when it gets back and reflects back up, it's bouncing like this. Those polarizations don't match. The light goes in, the light doesn't come out. If we have light going in that doesn't come out, what do we get?
Darkness.
We get darkness. That's right. So by simply turning this on and taking the power off, we make this go away, and we can see the light reflecting back. So basically, an LCD is a liquid crystal display. Those liquid crystals cause light to be polarized. When they do that, they block the reflected light, and you don't see the reflection, and it looks like it turns off. So utilizing ambient or backlighting in order to do that.
You mentioned quarter wavelength.
Yep.
Quarter wavelength of what?
Quarter wavelength of light.
Oh, okay.
Yeah, that material is really thin.
Okay.
Which of the following types of connectors is used for audio signals in amateur radio stations? That would be an RCA phone or phono jack. Those are the old school ones that for audio are red and white. For those of you who have, let's say, a turntable or have owned a turntable or a stereo cassette deck like I have, or a CD player going back about 30 years, you had your red and white plug. Those are your phone jack.
I still have my 8-track.
Oh, there you go. Do you have a reel-to-reel?
I have a reel-to-reel.
Oh, there we go. Okay. A PL259. Again, this is known also as a UHF connector. Terrible for use at UHF. That's why we limit them to 150 megahertz. So PL259 and an SO239 is the mating connector. We only use to 150 megahertz. An N connector is water. It's basically sealed from the atmosphere. It's got a rubber gasket, and it's good to 10 gigahertz. An SMA connector is a teeny tiny thing that you will often find on every handheld these days. And I don't know if you can see my picture or not, but basically I'm holding it up. Can anyone see that?
Yep.
Okay, this is an SMA connector. You may recognize these. These are actually fabulous connectors. They're threaded and they're good up to several gigahertz. They work very, very well. Okay, where were we? There we are. Okay, we are now into practical circuits. All right, a half-wave rectifier. So a simple power supply uses a diode. A diode conducts in the forward direction. If I have a waveform that looks like this, when it goes positive, I get the waveform producing energy on the output. When it goes negative, I get nothing. This is half-wave rectification. If the whole thing is 360 degrees, this gives me 180 degrees of the waveform. That's known as half-wave rectification. If I were to take this circuit instead and build a different circuit using 4 diodes, I would go like this. Here's my circuit. I'm going to go this way. And then for the other half of it, I'm going to go like this. I'm going to get up to here and go this way. Goes through 4 diodes. This is known as a diode bridge. There are 4 of them. And notice the black ones conduct, if you follow the path, they are both turned on going forward in one direction, which is when the plus is over here, but when the plus flips to the other side, it actually follows the backward path and gets blocked. So what ends up happening is that I end up with a voltage that looks like this. And the benefit of that is that I'm always converting my power. And this is known as full wave rectification. It allows me to use the full 360 degrees of the waveform. So it's a more efficient way of building a power supply. That's actually how most power supplies work. And that's known as full wave rectification. Okay, the advantage of a half wave rectifier only requires one diode. What type of rectifier uses two diodes and a center tap transformer? Okay, so I could do it with a transformer as well, and that would also be full wave rectification. But then I would need a transformer. The output waveform of unfiltered full wave rectification connected to a resistive load. So I'm going to draw that output again. It looks like this. If the original wave that went in was 60 hertz, what is the output waveform frequency? I get
120.
it's 120 hertz. I get twice as many pulses. 1, 2, 3, 4, 5, 6. And it's basically pulses, and without filtering, it sounds terrible. It looks awful. You never want to feed that into an actual device. Okay, next. What are used in a power supply filter network? Capacitors and inductors. A power supply bleeder is a small resistor that goes across a filter capacitor. Normally it doesn't do anything, but when you shut the power supply off, it allows you to it automatically discharges the big capacitor, which would give you a nice shock if you stuck your finger in otherwise. A switch mode power supply is a power supply that instead of working at 60 hertz, it actually creates DC and chops the voltage into and makes very high frequency components. So let's say it operates at 20 kilohertz. Because your components are frequency dependent, if you increase the frequency, you can use smaller components, which means that a 25 amp power supply, instead of having a transformer that weighs 40 pounds and all the accoutrements that go with it, so you have a 50-pound power supply, you can make a switching power supply, which basically uses transistor switching to generate a high frequency, and the whole thing for 25 amps weighs 3 pounds. That's exactly what we use to power our computers. We talked about this a little bit yesterday. Everyone, we're just going to start at number 1. What's number 1?
The field effect transmitter?
That is a field effect transistor. Okay, number 2, all the way on the right.
NPN.
ETL.
Yep. And it's an NPN bipolar junction transistor. Okay. Number 3.
A diode.
A diode.
Yep, that's a diode. Number 4.
A special diode.
A special diode, but we're just going to say it's a diode. That might be a Schottky diode or something. Number 5.
Voltage variable capacitor.
Zener diode.
Number 5 is a Zener diode. Okay. Number 6, upper right.
Solid core transformer.
Yep, that's a transformer. Okay, and number 7 at the left, bottom left.
Tapped coil.
That's a tapped inductor. Notice that that's a variable value inductor. And why would we ever do something like that? In case we ever had a circuit that we wanted to change the value of inductance. Okay, number 8. Up top, what's number 8?
The weird capacitor.
Yeah, it's a little bit of a weird capacitor. Schematics can be like that. Okay, and how about number 11?
Resistor.
Yep, but what kind of resistor? Notice it's
tapped?
got that's a tapped resistor, or otherwise known as a
Variable resistor.
variable resistor, or a potentiometer, or a pot. Okay, the next thing we're into
Wait, what
is
did we say about number 4?
number 4. The number 4 is, well, I mean, it's a diode. Did anyone have a specific kind of diode for that?
I thought it was a voltage variable capacitor. Is that right?
I don't know. I'm gonna have to check.
Number 11 was what now?
Number 11 is a pot potentiometer. Okay, digital circuits. Okay, so we are now moving into the realm of ones and zeros. So what we're going to do is one of my favorite things about electronics, the fact that we can take transistors and we can slam them full on and full off and make them either have values of 0 or 1. So we're going to have two things. We're going to have Yanni and we're going to have Scott. Okay, so Yanni and Scott are involved in a decision-making thing here. All right, so we're going to have Yanni saying either no, the no is a 0, or 1, which is a yes, and Scott doing the same thing. Our function here is that Yanni, if both of us say yes, the answer is yes. That would mean that if Scott and Yanni both agree, it's Scott and Yanni say yes. Okay? So if Scott says no and Yanni says no, what's the answer?
No.
No. If either one of us says no, but the other one says yes, what's the answer? No.
Yes.
No, because it has to be Scott and Yanni agree. So what's the only way that Scott that the answer is yes? If
They
Scott
They both say yes.
and Yanni agree. This is an AND circuit. It is represented like that. That's an AND gate. So now we're going to change this. We're going to say, we're going to have a new rule. If either Scott or Yanni say yes, the answer is yes. Okay? So what if we both say no?
No.
No. How about if either of us says yes?
Yes.
Yes.
How about if both of us say yes?
Yes.
Yes.
That's fine. This is an OR gate. That's the representation for an OR gate. So this is an AND, that's an OR. Okay? How about if we decide that we're going to have a...
Hold on, your drawings look very similar. I'm trying to understand the difference of the drawing.
I'll exaggerate it a little. That's an OR. It has
Is it
that.
just indented?
Yeah, it's
Is it
indented.
significant which
It's
way
indented.
the lines touch or don't touch the lines?
Okay.
The
Got it. So
horizontal
it's a little
lines
more
touching the
indented
D?
where the and is like a straight
The
D.
AND is flat. Yeah.
Okay. Thank you.
Uh-huh. So let me fix that. Okay. So now we have another one. We have, let's say that if either of us says yes, then the answer is yes. But if neither of us say yes, the answer is no. And if both of us say yes, the answer is still no. In other words, we have to have competing answers. So what if the answer is both no?
No.
That's no. How about if the answer is both yes?
No.
That's no. Only if one of us is different from the other, and that's actually called an XOR. That's another gate. So there's all kinds of stuff that we can do with this. So digital logic is basically just transforming decisions into ones and zeros. So what's cool about this is if we can say, okay, well, we have Scott, these are our inputs, and Yanni, those are our inputs, and we can go this way, and we can say a yes, but we can also take this signal and go into here, and we can say or, like that, and we can take these, and we can put these, and say, okay, we're going to take an AND of these, And then we're going to do an invert. So if we had a 1 here, we'd get a 0 here. If we had a 0 here, we get a 1 here. That's a NOT gate or an inverter. So we can add together all of these different logic functions and make some pretty complex logic. This is the basis for digital logic. This is how our computers work fundamentally. So we have our 2 input AND gate. We could actually have 6 inputs. We could have a 6 input AND gate, which looks for everything being true, and only if everything is true do we do that. Okay, so a NOR gate is similar to an OR, except that then notice it's a NOR, which is a not OR. So that basically flips the output. So the output is low when either or both inputs are high. High means true, low means false. So here's another way we can do cool stuff with digital. So clock is the input into the whole thing. That's CLK. RST is reset. The clock is a pulse. When the pulse comes in, this actually causes the Q output. This causes the D output to drive the next one, which causes the D output to drive the next one. And this is a binary counter. This actually cycles whenever a clock happens. If we look at the outputs, ABC, it starts at 0, 0, 0, 0, 0, 1 is the next one, 0, 1, 0, 0, 1, 1, all the way up to 1, 1, 1, and then it cycles back to 0, 0, 0. This is a 3-bit counter. And what's cool about that is that there are 8 different values, or 2 to the 3rd power. So if I did a 10-bit counter, I could represent 2 to the 10 different things, which is 1,024 different values. If I had 20 bits, I could represent 2 to the 20th, which is roughly 1 million different things. Okay. So that's digital logic. A shift register. That's a clocked array of circuits that passes data in steps. It basically moves it from point to point. It shifts it to the left. It shifts it to the right. If we have a value, for instance, if we have, let's say, 20 bits, or let's say 4 bits, we have 0, 0, 1, 0. Boy, that's terrible drawing. I got to learn to draw with my mouse better than that. Here, we have 0, 0, 1, 0. If we did a shift to the right, we'd get 0, 0, 0, 1. It would actually move the 1 to the right. If there was an input that said shift it to the left, we'd get 0, 0, 1, 0. If we shifted it to the left again, we'd get 0, 1, 0, 0. Somebody might continue shifting and say, oh, I'm going to add something from off the page. It would go 1, 0, 0, 1. So that is how binary logic works. Binary data. Binary data has only 2 values, 0 and 1. Okay, we're now into oscillators and amplifiers. Basic components of a sine wave oscillator. Well, if we have an amplifier, which is basically, we're going to say a transistor in this case, a transistor looks like this. Yeah, it's an op amp. I'm not going to do an op amp. And we take some of the output and feed it back into the input. And we have this and this. That makes it work at a certain frequency. And we take some of the output and feed it back into the input. It will go around and around and around and get bigger and bigger and bigger. That's known as an oscillator. And the frequency of oscillation is going to be defined by the inductor and the capacitor. So that's a positive feedback loop. And everybody has heard this. If you've ever been near a PA system where the speaker was too close to the microphone and it went, the question is, how did it pick that frequency? And the answer is because of where the speaker is and where the microphone is and how fast the circuit worked. You know, the feedback, you didn't pick it. It just happened. What determines the frequency of an oscillator? That's the inductance capacitance that's in the tank circuit. The tank circuit is sort of like if you want to think of it as a tank, it's sort of like the source of the energy. What describes a linear amplifier? Linear means that an input is replicated nicely as an output. So we have 3 ranges of operation of our transistor. Everybody remember that? 3 ranges of operation. We have cutoff, we have saturation, and in between we have the active or linear region. So if we use this area in between, if we have a change, we will get a proportional change on the output. So if we have a change of our input voltage, we'll get a proportional change on our output. That's linear. That is how we replicate something into something else. Make a bigger copy of it, because an amplifier does that. Now, one problem is if we say, okay, we want to place this right in the middle so that this is our 0 signal point. Well, what did we have to do that? We had to shift our 0 point from here over to the right. Our 0 point is also shifted way up here. That uses power. This is known as a Class A amplifier. Class A amplifiers are really clean, but they're also very inefficient. So what we can do is say that we're going to choose to bias our transistors, and instead of just one, now we're going to pick 2 of them. We're going to take one of them and shift it down so that it operates like that, and another one and shift it so that it operates like this. And we're going to move this so that what we basically get is that when one of them operates, darn it, I didn't mean to delete that. Here we go. Let me redraw that one right there. So that one of the transistors handles a part of it, and the other transistor handles the other part of it. And this crossover point is chosen such that this transistor handles the top part, and this transistor handles the bottom part. And our 0 line is actually right here. This would be known as a Class AB amplifier. And because you don't have to do a lot of biasing of your transistors, you can basically leave them mostly off. This is a much more efficient way to replicate a signal. But it requires 2 transistors instead of 1. Another way to build this amplifier is to say, okay, well, I'm going to just do this. And when I get a signal in, I'm just going to slam it full on. To heck with the amplitude. I'm just going to slam it full on. Well, that makes kind of a mess because it looks like this. Right? It's either on or off. That makes kind of a mess. Well, you could take this and you could actually run it through a filter, and you can actually generate something that looks a lot smoother. The other thing is that you could also take that signal and send it to another station, and once you do your filtering, you would just basically say, okay, I'm just going to take everything below this certain line, so it really doesn't matter what happened. I'm just looking at the frequency anyway. I want to see what my frequency is. This is actually like a Class D amplifier. And that's actually useful for FM. Because when we're dealing with FM, all we care about is the frequency. We don't care about the amplitude. So that's a much more efficient way of dealing with it. Unfortunately, again, if you're looking for linearity, that is not a good amplifier. But it's very efficient if you're doing FM. So for something for FM, again, you could also use Class C. Class C is sort of halfway in between. It's very efficient, and it tends to be useful for FM and not a lot else. So Class C, Class D amplifiers are good for FM. How is the efficiency of an RF power amplifier determined? You divide the output power by the DC input power. So if I have a 50-watt amplifier and it took 100 watts of electrical energy to make it run, I get 50 watts out. Divided by 100 watts in, I get 50% efficiency. Okay, the reason for neutralizing the final amplifier stage of a transmitter. If you have multiple transistors or multiple tubes, they have stray capacitance and stuff like that. And internally, they can have some inductance, they can have some capacitance between them. And what happens if you have a capacitor and an inductor? What does that make?
Resonant circuit.
Resonant circuit. So you can have an oscillator forming inside your amplifier. What frequency is it going to work at? I don't know. I have no idea. So what you do is this process called neutralization that eliminates self-oscillation of an amplifier circuit. You only want to amplify the thing that you put into it. Okay, so now we're talking about filters, things like that. So you have a filter. Ideally, it looks like this. That's a filter. The frequency at which it stops working is known as the cutoff frequency. And in reality, the points are the half power point. That's the cutoff frequency at the half power points. So, how many dB is half power?
3.
Minus 3 dB. Right. So we call this our 3 dB power point. Okay. What should be the impedance of a low pass filter? So let's say I have a 50 ohm transmission line and I have a low pass filter which has a function that looks like that. Low pass filter. There we go. Low pass filter. Zero frequency and infinity. This is 50 ohm cable. This is 50 ohm cable. What should the impedance of my low pass filter be, you think?
50 ohms.
It should be 50 ohms to maximize power transfer. Okay, the bandwidth of a bandpass filter is measured between what two frequencies? We just kind of drew this. So here's my bandpass filter. Here's the half power point. This is my bandpass width. This is my pass band bandwidth. And it's measured between the lower and upper half power points. The ability of a filter to reject signals outside the passband is called ultimate rejection. And because nothing is ever ideal, an ideal filter would have a bandpass value about like that. Notice that this is a little bit lower. This is called insertion loss. In other words, by putting it in, you actually reduce your signal just a little bit. And what do you think? What units do you think you measure that in?
More dBs.
More dB. So in order to compensate for that, let's say you have a narrower filter, like I've bought filters that are like this, that look like that. That has more insertion loss. So how do you make up for that?
More power?
Yep. basically there's a little amplifier that you switch a jumper plug and it changes the gain of the amplifier that's putting information into that filter to compensate for it. Okay, what circuit is used to combine signals from a carrier oscillator and speech amplifier and send the result to a filter in some single sideband phone transmitters? This is known as a balanced modulator. Essentially, it's a mixer, but allows you to generate just a single sideband signal. So just got to remember that's called a balanced modulator. Which of the following is used to process signals from the balanced modulator and send them to the mixer? Got to run it through a filter. What is used to process signals from the RF amplifier and local oscillator and send the result to an IF filter in a super het receiver or super heterodyne? That's a mixer.
You leaving?
Sorry. I'm not going anywhere. Okay, the simplest combination. What circuit is used to combine signals from the IF amplifier? IF is intermediate frequency, and BFO is a beat frequency oscillator, and send the result to the AF amplifier in some single sideband receivers. Okay, so what we're going to draw is we're going to have an input from the IF. That's an intermediate filter. And we have a BFO, and this puts out signals to a speaker. Okay, what is this device called? This is called a product detector. In reality, what is that product detector? What is that symbol? You remember from yesterday?
It's a mixer.
That's a mixer, yep. So a mixer being used to detect audio is known as a product detector. So if we were to combine two different higher frequencies, we would, call it a mixer. The simplest combination of stages that implement a super heterodyne receiver. Well, we have our input. It goes in through a mixer. We have an oscillator. We call it local oscillator. Excuse me. This generates a frequency. We would put this through a filter to get the frequencies we want. We'd run this through a product detector. And what's another one? What is a product detector?
A mixer.
Yep. And run that into our speaker. That is a basic block diagram for, and actually we'd probably put a filter here too. That is a basic block diagram for a very simple receiver. Okay, so HF oscillator, mixer, detector. What circuit is used in analog FM receivers to convert IF output signals to audio? That's known as a frequency discriminator. And so because FM is kind of a weird thing, it looks like this. A discriminator, because the amplitude is always going to be the same, is just basically looking for differences in frequency from a central point. So this is normal. This would be high. And this would be lower frequency. A discriminator would basically say, okay, well, my frequency is changing and here's how it's changing. And I'm going to convert that into audio. What is a direct digital synthesizer? Well, a sine wave, if everyone agrees, looks like this, right? Everyone agree that a sine wave basically looks like that?
Okay.
Yes.
Okay, so if I were to take this and I drew a picture that looked like this with dots. Is that basically a sine wave?
Yes.
Yes, and in fact, if I run this through a filter, I will get a nice clean sine wave. Now, what's cool is that these dots are actually just stored in a computer. The values of those dots are stored in a computer. And these are used to generate a voltage, each one of them. So because they're stored in a computer, It's direct digital synthesis. It's actually generating something that looks like a sine wave from a bunch of digital values. Now, if I ran them faster, I could make it look like this. Here's my dots. I just made it go through the dots faster. What's cool about that is that here's my new sine wave. It's made from the same data that's in the computer, except what's different about it compared to the one on top?
Higher.
It's a higher frequency. So basically, by changing how I read the data and pull it out and make a copy of my sine wave, I can make a different frequency sine wave, pretty much any frequency I want, and that's known as direct digital synthesis, or DDS. So it's a way of synthesizing a frequency without actually using capacitors and inductors. You basically will just generate it from computer-based values. So high stability variable frequency oscillator in a transceiver is usually done with a DDS circuit. It's a digital thing instead of an analog thing. Advantage?
No hardware, it's just a computer making a signal?
Yep, that's what it is. And as computers have become faster and faster, the DDS circuits have become better and better and better at making clean signals. So the nice thing about it, variable frequency with the stability of a crystal oscillator. A crystal oscillator is literally a piece of quartz crystal that vibrates at a given frequency. And because it's solid, it doesn't change a whole lot, so crystal oscillators are typically really stable. Well, this allows you to generate a variable frequency, whereas a piece of crystal is just a piece of rock. You can't change the frequency on a piece of rock when you vibrate it. What is meant by software-defined radio? A software-defined radio is a radio in which most of the processing is done by software internally. That includes receiving. That includes amplification. That includes filtering. They're all done by a computer. And because of that, the computer replaces all of those intermediate filters that you would otherwise have to build. It's all done in software. Everything's converted into a string of ones and zeros, and it's run through a really, really fast computer. And then you get audio out. Kind of like magic. Okay, the phase difference between the I and Q signals that a software-defined radio uses for modulation and demodulation. Just important to know that I and Q are 90 degrees apart. They're perpendicular. The advantage of I and Q signals in an SDR is that all types of modulation can be created from just those two signals. All right, signals and emissions. Okay, so this is what AM looks like. That's amplitude modulation. AM is the waveform connected by connecting the peak values of a modulated signal. If you filter out one of the sidebands of an AM signal, you get one sideband. If you push the signal too hard, you get something called flat topping. So let's say that I am going to have an amplifier, and I do this with it. Here's my transistor, and my transistor does this. And here's my linear region of my amplifier, and I push my signal so far, because I'm yelling into the microphone, that it gets to here. Am I still in the linear range? This is the linear range.
No.
No, I am not, which means that I am getting distortion. Basically, things that are not made as a copy of what's going in sound like distortion, and that's known as flat topping, and it causes distortion. And when you do that, when you overmodulate, you'll get excessive bandwidth. It tends to splatter all over the band. Everybody will notice that. The name of the process that changes the instantaneous frequency of an RF wave is called frequency modulation. The name of the process that changes the phase angle is known as phase modulation. A reactance modulator, we covered this yesterday, connected to a transmitter RF amp stage is phase modulation. frequency shift keying. Basically, depending on what's happening, if I were to do frequency shift keying, I would get something that looked like this in time. I'd get this frequency, and when I got a value of 1, I would shift to this frequency. If I get a value of 2, I shift to this frequency. Get a value of 3, I shift to this frequency. So in time, I have something that might look like a player piano tape, if you looked at it on a display. And in fact, that's really what it looks like. If you look at a signal on a waterfall display, a waterfall is time versus frequency. It basically advances in time. You will actually see and it goes from top to bottom usually. If you're looking at FT8, it'll look like something like this. FT8 is a frequency shifting system. It'll actually look like a player piano tape. Okay.
Play the piano, it really is just the opposite way. It's programming paper to operate strings.
That's right. It changes the tone.
system,
It's the
different
exact
day.
same thing. Okay, QPSK31. PSK is phase shift keying. Quadrature phase shift keying is the Q. It allows you to have 4 different values instead of 2 different values. 4 different phases. It's important to note that because it's quadrature, you can go to 1, 2, 3, or 0, 1, 2, and 3, or 1, 2, 3, and 4. It's sideband sensitive. If you flip to the wrong sideband, you'll be going the wrong way. Encoding does provide error correction, and its bandwidth is approximately the same as BPSK31. Okay. 8-tone frequency shift keying is FT8. That's why it's called FT8. It's a very low signal to noise ratio mode. It's great for very low data rates, really low data rates, but being able to communicate over immense distances with almost no power. Mixing of 2 RF signals is called heterodyning. Combination of a mixer's local oscillator and RF input generates the sum and difference. We talked about that. The mixer input is varied or tuned to convert different signals of different frequencies. That's called the local oscillator. That's the oscillator that you have control over. Okay, so image response. In order to understand this, what we need to do is look at a mixer and say that we have frequency A and frequency B. Okay, what values come out of that mixer? A, B, A plus B, A minus B, B minus A, 2A, 2B, etc., etc., etc. Well, so let's say that we have one frequency that's right here and one right here, and we want this one. Well, we also will get one minus the other, which will come up over here. We also might get one over here. If we mix them together and this is the one we want, this one might be the image, which is an unwanted component. So the image frequency would show up, for instance, if I had a value of 14 and I mix it with 0.2. What do you get if you add those together? 14.2. What do you get if you subtract them?
12.8.
13.8.
13.
Right? This is the image frequency on the left. This is the desired frequency. If you don't have good filtering, you'll actually be able to tune your radio to a different frequency and hear the image. And you typically don't want that. Okay, that's known as image response. So if you look at the math in here, receiver mixing 13.8 with 14.255, you'll get the sum and the difference. So in this case, this one, 13.345, mixes with 13.8 to generate that same 455. So it works in both directions. If you have two signals coming into a mixer. Notice it says nonlinear circuit. A mixer is a nonlinear circuit. They modulate together. They actually mix. So this actually is something that I have experienced before. So I had a tower which had some rusted connections. Well, a rusted connection can act as a diode. A diode can be a demodulator, believe it or not. It can also be a mixer. I had a station nearby which was at 1580 AM and another one that was at 980 AM. Those are in kilohertz. So what's 1580 minus 980? 600 kilohertz. What is a repeater offset on 2 meters?
600 kilohertz.
This was then mixing with 144.89 megahertz, or sorry, 145.49 megahertz, and I was getting, this is in megahertz, this is 0.6 megahertz, and I was getting 145.8.49 minus 0.600 and getting 145.89, 144.89. And this is our receiver's input frequency on our repeater. So these two stations combined with our transmitter were causing intermodulation distortion and interference, which was generating a signal which would basically go back into our repeater input. That was a hard one to figure out. That's intermodulation distortion.
So how did you figure it out? And then did you climb the tower and clean it up?
Yeah, we did. And we figured it out by listening to the signals that were coming through the repeater, and we could actually hear a little bit of AM modulation on it. It actually sounded like an AM station. Okay, FM transmitters use multipliers to produce a VHF signal. So if we have a multiplier, that means we basically start with a baseband frequency. If our target is 144 megahertz, we could start with 12 megahertz, produce a signal that looks like this. When we use a frequency multiplier, it multiplies everything by 144, so everything gets 144 megahertz wider, or 12 times wider. So if we want a signal that is, let's say, 12 kilohertz wide, we will make a signal that is 1 kilohertz wide. That's our desired signal inside what we're transmitting. So that's how a frequency multiplier works. We're just making it wider. So the frequency deviation for a 12.21 megahertz reactance modulated oscillator in 5 kilohertz deviation. 5 kilohertz deviation means that if we divide it by 12, we get 416 hertz wide. So when we make our signal, it only has to be 416 hertz wide. Then when we spread it out by a factor of 12, it becomes 5 kilohertz. Okay, so this formula you just need to know. If you see this question, a phone transmission having 5 kilohertz deviation and 3 kilohertz modulating frequency, that will make 5 plus 3 is 8, and it goes above and below, so you'll have a bandwidth of 16 kilohertz. That's just something you have to memorize. This is where it becomes a little more complicated because there's some things you just have to memorize. PACTOR 3, maximum signal rate, maximum bandwidth, 2300 hertz. That'll fit inside a single sideband signal. PACTOR 3 is a digital mode over single sideband. This is another one of those you just have to memorize. Why is duty cycle important? Some modes have a high duty cycle, some have a low duty cycle. If you have a transmitter that is designed for 100 watts output intermittently, and you basically just put you take your Morse code key and you put a brick on the key, and it's designed for 100 watts intermittently, and you're trying to get 100 watts continuous out of it, you'll end up damaging the transmitter. So it's important to know what duty cycle is. What is the difference? Oh, so if you think about a repeater, if people are having a conversation on a repeater, How much time is that repeater spending transmitting? How much of the time?
All the time.
All the time, 100% duty cycle. So if you have a repeater transmitter that's designed for 50 watts, it better be designed for 50 watts with 100% duty cycle. So big heatsink and the ability to stay and run all the time. Most individual transmitters are not like that. So that's why you need to specify that. Transmitted symbol rate and bandwidth. Higher symbol rates require more bandwidth. They take up more space. Why is it a good idea to match receiver bandwidth to the bandwidth of the operating mode? If you can eliminate the external frequencies that you're not listening to, you don't have all that extra noise coming in. So you get a good signal to noise ratio. Okay, PSK 31, it takes up 31 hertz. It's also the approximate transmitted symbol rate. We covered this yesterday, that PSK 31 is something called varicode, which means that the lowercase letters take fewer bits to encode than uppercase letters. That's why people usually will transmit PSK 31 in all lowercase. Here we go, Baudot code. So this is baud. Baudot is a 5-bit code with additional start and stop bits. There you go. That's Baudot. 2 separate frequencies of a frequency shift keyer station are identified as mark and space. If you use radio teletype, those are known as mark and space. Digital mode used as a low power beacon for HF. That would be whisper. It's weak signal propagation report. You basically just send out beacons of information saying, here I am, here I am, here I am. And everyone who can hear you will report it. So it allows people to develop a map of what the world looks like on the air. A packet radio frame that contains routing and handling information is called the header of the message. PACTOR again. A NAC packet means I didn't get it. So NAC literally stands for no acknowledge.
So before we get too far away from RTTY, what do we actually use RTTY for, and how do we create a signal that's going to be transmitted by RTTY?
RTTY is radio teletype.
Right.
It used to be that people would actually have teletype machines hooked up to the radio.
So is it now just all digital?
Yeah, it's all on the computer now, thank God. You're not spitting out reams and reams of paper. If there are too many retransmission attempts, too many NAC packets using PACTOR or WinMore, those are both digital modes on HF, the connection gets dropped. And it's important to note that on packet, again, a NAC packet is very similar to something called ARQ, automatic repeat request. Forward error correction. If I were to send, let's say that I was sending my name and I said Scott Bob, or you copied Scott Bob, what would you figure out my name was? Oh, Yanni, you're muted.
Okay, I guess Scott Bob.
Well, no, if I said, okay, I'm going to send my name 3 times. I said,
Oh,
Scott Bob. What's my name probably? Right.
Scott.
Right.
For Scott.
Right. So you send redundant information. So that's what forward error correction is. Now, because I had to send it 3 times, that means that some of the time was spent with that redundant information, which kind of wastes some time. But if your goal is to get the information through, it's okay to do that. A waterfall display, frequency is horizontal, signal strength is intensity, and time is vertical. You can find a waterfall display on that on the link to the web SDR or any of the web SDRs. You can take a look at the waterfall display. If you have vertical lines on either side of a digital signal, that means you're driving it too hard and you're driving it into overmodulation. On what band do we share channels with the unlicensed Wi-Fi service? There's actually 2 of them. The one that's the answer here is 2.4 gigahertz. We actually share it with 5.8 gigahertz as well. Okay, so now we're into antennas and feed lines. So if we have two antennas that are separated by a distance, what does that look like? Or two wires that are separated by a distance? That makes a capacitor,
Inductor.
doesn't it? That makes a capacitor. So spacing, and each one of these is a piece of wire. Piece of wire has inductance. Because they have inductance and they also have a space between them, that means that the spacing and the size of the wires determines on a parallel line what the characteristic impedance is. They have an L and a C. I can do the same thing with a coaxial cable. That has a capacitor right here, and it has conductors, so that makes an L, so I have an L and a C. If I change those values, I change my characteristic impedance. The most common ones that we use for radio are 50 and 75 ohms. 75 ohms is typically used for cable TV. I don't know why, but it also means that if you can use 75 ohms cable, there's no reason you couldn't. It's pretty close to 50. It's really, really, really cheap. You can get lots of it for almost nothing. What can cause reflected power where a feed line connects? You could have a difference between the impedances. If you have an impedance mismatch, you get reflections. A perfect match is a 1-to-1 standing wave ratio. That's a perfect match. Okay, so this is just a simple calculation. If you have standing waves on an antenna feed line, to eliminate those, you have to match the load to the feed line. 50 ohms to 50 ohms, perfect match. How about 200 ohms to 200 ohms?
Perfect.
Perfect match. Okay. How about 200 ohms to 50 ohms?
Okay.
Not a perfect match.
4-to-1.
Yep, 4-to-1. You basically divide the bigger one by the smaller one. So what if you had a 50 ohm and a 10 ohm?
5-to-1.
5-to-1, because one is 5 times bigger than the other one. Either way, that is a very poor way to match your power and get your power to your load. Okay, this is a fundamental question. This is why I'm going to do this one. If the SWR on a feed line is 5-to-1 and a matching network on the transmitter end of the feed line is adjusted to a perfect 1-to-1, what is the SWR on the feed line? And the answer is 5-to-1.
5-to-1.
It didn't fix anything. It did not fix your mismatch. What did it do? It made your transmitter happy. That's all. It made your transmitter happy. It won't blow up your equipment, but it doesn't fix the underlying problem.
But what difference does that make? Your transmitter's happy, but your power is still not going out efficiently into the
Correct.
antenna?
Now, here's the next thing. If a transmission line is lossy, your signal bounces up and down the cable multiple times. The lossier the transmission line, the more impact your SWR will have, because you have to make more and more trips up the line. If you have really lossy line, you might be able to put 100 watts into your power, into your system, but maybe you're only getting 10 watts out. Your transmitter is perfectly happy, but how much power do you have going out? Very, very little.
So what's the point of a circuit like that in a transceiver if the circuit that is designed to make your transceiver happy is really not making any difference in fact in the signal? Why is that circuit always there?
Well, because it's better to have your transceiver happy than not happy, right?
Where does all that extra energy go? To heat?
Heat. Yep.
So your transmitter's happy and your wires are frying?
Yep. Your cable's getting hot. Which is why it's important, if you're going to have something with high SWR, if you have cable that has low loss, it's really okay. We did a little example of that yesterday after class, and that's why I use ladder line, because ladder line is really low loss cable. So even if I have a really bad SWR, I can still get away with it really well, because the loss is so low that it virtually makes no difference.
Are we doing a lunch break today?
We're going to go to noon, and we're going to pretty much stop. So Okay, so the higher the okay, what is the effect of transmission line loss on SWR measured? The higher the loss, the more the SWR will read artificially low. The reason being that an SWR meter reads power coming back. If all your power got burned up as heat, well, it didn't make it back, right? So if your cable is really lossy, it might look like a 1-to-1 SWR because nothing's actually making it back. Okay, we did this one. How does the attenuation of cable increase as the frequency goes up? Attenuation goes up, measured in decibels per 100 feet. So if you have, let's say, a really small cable that has very high loss per 100 feet, but it's only 3 feet of cable, it might be perfectly okay.
22.
Ladder line, notice 450 ohms. What kind of a match is 450 ohms to a 50 ohm antenna? What SWR would that give you?
9-to-1.
9-to-1, yes. So it might be a good idea to install a 9-to-1 matching transformer, which would match those. Okay, basic antennas. If you touch a metal object, not even just the antenna, if you touch a metal object in your shack, you may get an RF burn. So the reason being, what we're going to do right now is just briefly draw the difference between ground and ground. Okay, everybody agree that that's a ground?
Mm-hmm.
Okay, that's ground. Now, let's say that I have, at 60 hertz, I have grounded my equipment. Okay, so here's my radio. It goes up to my antenna. Okay, at 60 hertz, here's my radio. At 60 hertz, this is my power coming into it. What is the wavelength of 60 hertz? It's 5 million meters long. Right? 5 million meters is basically coast to coast. That's the wavelength. So in other words, this connection could be from my transceiver through the power line, through my house wiring. This could be 125 feet, and it's ground. Ground is ground, right? Okay, now let's look at it from an RF standpoint. Let's say that I am operating on the 6 meter band. What is the wavelength on 6 meters? It's 6 meters. It's 20 feet. What do I know about ground? Ground is at 0 volts. This is 125 feet. I have this on my ground wire. Is there any guarantee that I have a 0 volt point at my station?
No.
No, there is not. That's why station grounding, they want to keep the wire really short and go to its own nearby ground. Don't use the house wiring. It's also true that if you use an N-fed wire, for instance, an N-fed wire can also, or a random wire for that matter. Let's go with a random wire, I think, in this case. If you use a random wire antenna, you can actually generate, for the same reason, a fair amount of RF energy on your equipment. You lean over, you touch your mouth close to your microphone, and you get a shock from your microphone, which is not 120 volts. It's an RF shock. And a lot of that is due to the fact that ground is not ground at RF.
So why do some people get more charged than others?
That I don't know.
Oh, because I seem to be charged no matter where I go.
Yeah, well, I'd say that's your internal body chemistry, maybe.
I must have a lot of minerals.
You might, yeah. Okay. Next. Okay, antenna calculations. Okay, we're not actually going to go through them, but I'll bet you guys can tell me how to calculate an antenna after all the stuff we've done. What's the first thing you do? How do you calculate frequency and how do you calculate antenna length from a frequency? 300 F lambda. You guys remember this from day number 1?
Yep.
Right? So we can calculate our wavelength, then determining how long the wavelength needs to be, whether it's a quarter wave or a half wave antenna. We can multiply that. And then what do we always have to take?
95%.
95%. That's it. That's how you calculate an antenna length. So whatever it happens to be, now you know how to calculate your antenna length. Okay, we covered this one a little bit. How does the feed point impedance of a half-wave dipole change as you move toward the end? The lowest impedance is going to be at the middle. If you have an end-fed antenna, it gets closer to that point where you have zero current. The zero current point is maximum voltage. Impedance is volts divided by amps, which means you're going to have a really high impedance. So as you get closer and closer to the end, it goes up and up and up and up. Okay. A horizontally polarized antenna compared to a vertically polarized antenna, your signal is going to have lower ground reflection losses if you have a horizontally polarized antenna. Radiation pattern of a dipole is a figure 8 at right angles to the antenna. So if you look at it from above, here's your dipole. It looks like this. That's your radiation pattern, looking at it from above. If you have another element that's about 5% longer, that's a reflector. That will take some of the energy and refocus it in the forward direction, and then you'll have a beam antenna. And what was the measure of the forward strength to the reverse strength? Remember what that's called?
Front back ratio.
Front to back ratio. So this is about 5% longer. This is about 5% shorter. The more things, this is called a director. The more things we add, the greater the front to back ratio, and the greater the gain of the antenna compared to the original antenna. Those are, again, measured in decibels. Okay, how does the height affect the horizontal radiation pattern? If your antenna goes lower and lower and lower, you lose your directionality. It becomes almost omnidirectional, which can be a good thing. Can also be a kind of a pain. The feed point impedance of a half-wave antenna, if it's below a quarter wave, goes down and down and down and down, which means that you're actually going to become less and less efficient. A quarter wave ground plane vertical antenna is something viewed from, let's say, the roof of a car. This is why we do this on the roof of a car. Here's the roof of my car. Here's my antenna. It's a single point. Does it know any difference between any of these directions? There's symmetry, which means that it's going to be omnidirectional in all horizontal directions, which is known as the azimuth. This is why we also, on repeaters, use vertical antennas, because, again, there's symmetry. Repeater doesn't care which direction is which. It doesn't favor any other. And since the antennas are both vertically polarized, the signals will all see each other. So that's why vertically polarized signals on VHF repeaters, UHF repeaters, are typically what is used. Okay, radials. Radials, because ground, if you think about it, a quarter wave vertical requires a ground plane, kind of like the roof of a car. What if you take a quarter wave vertical and stick it over your physical ground? What is your physical ground made of? It's made of rocks and dirt and some water in there. It's not necessarily a good ground. So what you do is you take radial wires, which are supposed to simulate a perfect ground, and you stretch them out or bury them just below the grass. If you have a ground plane vertical that looks like this, annotate. So this is a quarter wave ground plane. This has an impedance of about 36 ohms. 36 ohms is not 50, is it? I don't think it is. 36 ohms is 36. That's actually an SWR of about 1.5 to 1. However, you can do this with the radial wires and bend them downward like that at about a 45-degree angle, and that will raise your feed point impedance up to 50 ohms. The way to think about this is, why does this happen? Because what is this if I just take two pieces of wire that are a quarter wave each? What kind of antenna is that?
Dipole.
That's a dipole. That has an impedance of 72 ohms. If I take a vertical that looks like this, that has an impedance of 36 ohms. So this right here is about halfway in between. And that gives me an almost perfect match.
Was this
Is
above the
length
ground
of
or below the ground?
That's typically above ground. Like up on, a pole. Okay. Next. We're into directional antennas. A
Do
directional
those
antenna
wheels need to be anchored if they're above ground?
depends how you're building it. I mean, I just use solid wire, which supports itself.
Okay.
A directional antenna minimizes interference because you can reject areas. DBI refers to an isotropic antenna, whereas DBD refers to a dipole. DBI gain figures are always going to be 2.15 dB higher than DBD. Front to back ratio we covered. The main lobe is the direction in which the most energy is transmitted. How do you measure the main lobe bandwidth or the main lobe beam width? So here's the main lobe. Here's full power, and here's 3 dB down. This angle is known as the beam width. If you have more gain, your thing is more stretched out, and your 3 dB point would be here. So the higher the gain, typically the narrower the angle of the beam. Which means that with really high gain, it's really important to focus. Your antenna beam width is going to be really focused, and it's really important to make sure that you're pointed very carefully. Approximate length of a driven element is a half wavelength. Reflector is longer, director is shorter. To increase the bandwidth, you make your wires fatter. Sometimes we use aluminum pipe instead. And when you increase the boom length and adding directors, you get more gain. If you take two antennas and stack them about a half wave apart, they are now operating together. It is now double as good. If it's double as good, how much gain do you get?
10 dB.
Nope. What is
3
two,
dB.
2 times? Is 3 dB. So by stacking two antennas above each other, you get a gain of 3 decibels. The advantage of vertical stacking is that it narrows the main lobe in elevation. It squeezes the signal down and gets your signal lower to the horizon. A gamma match? Okay, a gamma match. This is a gamma match. I have a solid piece of aluminum, and I have one point tied here and the other point tied right here. Wait a minute. How do I get... Doesn't that look like a short circuit?
Yeah.
Yeah, it's not. Because what do I have here? What is that? I have space. And what do we know about wavelengths and stuff like that? They are DC shorted together, but AC, they are not shorted together. They are two different places on that same piece of aluminum. And by doing that, this is known as a gamma match. That allows us to put our energy into here and keep this other point as a reference point. And by doing that, we can actually put energy into it and get a nice match. And you can use a solid piece of aluminum instead of having two pieces of aluminum, which is actually really convenient. If you're building something with, a 30-foot span of aluminum, you don't want to have it split in the middle. A quad antenna is basically a full size, it's one full wave in a pattern of a square. You can also do a loop that's in the shape of a triangle with one full wavelength of wire. A hairpin match is if you do happen to have power fed into a piece of into an antenna that looks like this. One feed goes here, one feed goes here. This is a hairpin match. It connects the two. Again, doesn't that look like a short circuit? Except that it has size. It has length, not a short circuit. At AC. It's a short circuit at DC, but not at AC. You have to sort of like suspend your reality a little bit and know that AC and DC are very, very different beasts.
Say that again, the AC is not shorted, but the DC is?
Yeah, well, you're not, and since antennas, you're not going to be using DC, it's not a short circuit. There's a physical piece of wire that separates them, and that allows them to be at different voltages for AC. There are different points on that wire.
AC is not short circuited, DC is.
Well,
Is that correct?
here, if I look at this, here's that solid piece. I'm going to feed this in the center, and then I'm going to feed the other part to way over here. That
Okay.
you would think those are short circuited, right? For
We're on AC
DC,
now or DC on?
for DC, that's a short circuit, isn't it? Except
Okay.
at AC, here's my waveform. Is this point right here at the same voltage as that point? Is it at the same current?
Current?
Is it? Are those 2
Different
points?
wavelengths.
Are they? Well, no. Are
different
those
what?
2 points at the same voltage and current? This one is right up here, and this one is up here. Are those at the same value?
No.
No. In other words, for AC, that is not a short circuit because they are separated by this length of wire or this length of aluminum. And that's why antennas are so freaking cool. Because the things that you think are true are not necessarily true. And you can do all kinds of cool stuff with them that don't make sense. But then when you think about it, yeah, it really does make sense. So a 2-element quad, again, a quad is a loop, is about the same as a 3-element Yagi. Quads are a little bit harder to build. An inverted V is a dipole that is supported in the center and droops down at the ends. A multi-wavelength horizontal loop is typically going to be omnidirectional with a low radiation angle. Just something you have to memorize. A log periodic we covered the other day. That's your old school television antenna. So element length and spacing vary logarithmically. It allows you to have immense amounts of bandwidth with very low gain. NVIS, if you have an antenna that's really, really, really close to the ground, most of the energy goes straight up into the air. If you're trying to talk to somebody that's up in the sky, or you're trying to have a high bounce to get a short skip, that works really well. A beverage antenna is a terrible transmitting antenna, but it's a great receiving antenna. It's a directional receiving antenna. That's the name. That's called a beverage. A multi-band antenna has poor harmonic rejection because by definition it's designed to receive many different bands at once. It works on many different frequencies. Therefore, if you transmit a signal that has a couple of different frequencies on it, the antenna might actually work at that frequency. The purpose of a trap is sort of like we did a little bit of a loading coil on an antenna. So this is a loading coil for an antenna. Now you could also design a system by which you have an antenna section and then you have a box. And inside that box is a capacitor in parallel with an inductor. Well, unlike this right here is a resonance circuit that allows all the energy to flow. If you put them in parallel at a particular frequency, this allows no energy to flow through it. So if I have an antenna that looks like this, like a vertical, at a particular frequency, the antenna stops at the trap. Literally, the energy gets trapped at that point, and my antenna length is just this part at the bottom. That's known as in this case, that's known as a trap vertical. Other frequencies, the rest of the antenna comes into play. So that's how you have an antenna that can work on multiple different bands at one time. Okay. electrically small loop, we have something called a mag loop. A mag loop is a very small antenna, usually a fraction of a wavelength. And it looks like this. So you feed power up here. This couples magnetically to the rest of this big loop. And it actually transmits along the wire and not perpendicular, which actually can be really helpful if you're trying to talk to somebody far away, because you have along the axis of the wire, you have really good coverage. So you can, because they're fairly lightweight usually, you can just rotate it 90 degrees and it works really well.
Okay.
Okay, a screwdriver antenna is basically a variable version of your handheld antenna. By changing the length of the coil at the base, that changes the resonant frequency. The reason it's called a screwdriver antenna is because that section at the bottom that does that is driven by a cordless screwdriver motor. A maximum radiation from a halo antenna. A halo is a horizontal loop, like you could picture a halo on top of someone's head. A halo transmits in the plane of the loop. Okay, radio wave propagation. We covered sunspot numbers. Solar flux is energy from the sun, which translates roughly to ionizing radiation levels. It's measured at 10.7 centimeters. This is measured by astronomical observatories. The sunspot cycle does not matter for the most part as far as the 20-meter band goes. 20-meter band is always good, at least to somewhere. When you have low sunspot activity, the higher frequency bands are the ones that fail first. So 10 meters goes, then 12, then 15 meters. And if we take a look at the frequency spectrum chart, we will see that. What causes propagation conditions to vary in a 28-day cycle? Well, the sun turns every 28 days. So if there's a sunspot group that's in one place, 28 days later, it'll spin around and be back to you. It takes sunlight 8 minutes to get to Earth. If there's an X-ray burst or something on the sun, it will take 8 minutes to get here. We can't possibly know that it's coming. However, if there is a particle storm coming, that usually takes between 20 and 40 hours to get here. We will know that it's coming, and we'll be able to at least, prepare a little bit. A sudden ionospheric disturbance will basically disrupt low frequencies really badly. Like to the point where I've actually been on the air and we had a solar storm happen, and it sounded like all the signals went away, and I felt like my antenna must have fallen to the ground. But everybody heard that. So the charged particles that are emitted by the sun, when they get to the Earth, they cause our atmosphere to basically fill with noise and absorb energy, and everything goes away. HF conditions completely disappear. A geomagnetic storm is a temporary disturbance in the Earth's magnetosphere. So high latitude HF propagation tends to go first. The reason being that geomagnetic clouds of particles, particles coming out of the sun, they typically enter the Earth's atmosphere at the poles. So the higher the latitude, the worse your effects are. Now, when there is an aurora, the same thing that causes an aurora, auroras, you can actually send energy into the aurora and listen to what comes out. And it sounds kind of ghostly and weird and distorted, but it's kind of cool. Okay, so now, if you look on, if you go to space weather, you will see that geomagnetic indices, there's something called the K index and the A index. The K index is short term over the last 3 hours. That's a level of how stormy our geomagnetic field is. The A index is an average of the last 24 hours. So basically what the K index has been doing for the last 24 hours. Okay, here's muff and luff. Muff is maximum usable frequency. Luff is lowest usable frequency. So the maximum usable frequency, you look at, you know, how the signal's getting from place to place, what season it is, and if your lowest usable frequency is below the muff, then you have a chance of getting signals up into the sky. So they're bent back to Earth if it's between the muff and the luff. So if you're below the luff, they are completely absorbed. If you're above the muff, those go straight on through. So there's this happy spot where you're between the two, at which point they will be refracted back to Earth. So occasionally, the lowest frequency exceeds the maximum frequency. This actually happens quite frequently. So let's say that I were to draw a picture of the Earth. That's bad. There we go. And I want to, here's the atmosphere, here's the ionosphere around it, and I wanted to talk to somebody way over here on the other side. Normally, to get there, I would have to go 1, 2, 3, 4, 5, 6, 7, 8. So 4 bounces to get there. And there's a section where on the frequency that I picked, it's really, really strong daylight, and the D layer is built up really highly. And because of the length of the path, let's say the maximum usable frequency for that path is 9 megahertz, and the lowest usable frequency is 11 megahertz. So in other words, the lowest frequency is actually higher than the highest frequency, in which case I have no signal path to get from here to there. If you're trying to talk to somebody on the other side of the Earth, this is actually very common. Okay. How do you maximize your signal? How do you, in other words, lower attenuation from getting to one point to another? If the maximum usable frequency is 22 megahertz, there's a good chance by looking at your frequency chart that 21 megahertz is where you should probably be. You want to be at a frequency just below the muff. Okay, let's go back to here. A way to determine if the muff is high enough to support skip propagation. There are international beacons out there in the world, and this is actually part of an international beacon program. They take turns transmitting from different spots on the Earth, and they'll have their own signal with a call sign and a location. If you can hear it on a particular frequency from a particular place, that's a good indication that the band is open, that you actually stand a chance. So if you have long path and short path, okay, there are actually, unless you are completely 360 or 180 degrees from another station on the Earth's surface, to go from here to here, this is the short path, and this is the long path. One full trip around the Earth takes about 1/7 of a second. So if this one gets there in 0.03 seconds, and this one goes 0.11 seconds, you'll actually hear an echo because they're coming in 2 different ways. I've actually been lucky enough to hear my own signal go all the way around the Earth. Okay, ionospheric layers, critical angle. How about a 5-minute break, everybody?
Okay.
Okay. Whew. Okay, and before we go back into it, let me ask for questions. If you're here and you've got a question, let's hear it.
I had a million questions. I don't remember any. I'm falling asleep.
You're falling asleep. Rough night?
Yeah. It's after 2 here and it's hot.
Yeah. Well, you know, you can move.
Yeah.
You do have a mobile house.
Yeah, that's right. You gotta grab the hose and
All right, so Yanni, I'm assuming you're not originally from Canada, correct?
I am from Greece.
I figured that. Yeah.
Yeah, I was born on a boat in Princess Island in Istanbul when my parents were circumnavigating.
Uh-huh.
I was born on the boat.
So you were born to sail, weren't you?
I think so.
Yeah.
I haven't figured it out yet, but I think so.
Okay.
I think literally you were born to
Born
sail.
to sail, yeah. So do you have a Greek license as well, or no?
No, I don't. That is where I first heard of the Exos and the Exos, and I was getting the magazine, and but I never got into it. So there we are.
Yeah. You were born on a boat. Wow. Everyone's got an interesting origin story. I was born in New York City in a snowstorm in a hospital.
I was born in the back seat of a taxi,
Were you really?
delivered by a great big black man.
They didn't make it, huh? They were
No,
on the-
didn't make it. And I was
Did
born
he charge
butt,
extra?
he did not. And I was
That's
born butt
crazy.
first.
Yeah, I would have been like, I don't know, bro. I gotta play doctor here. Like, I charge a couple bucks more per mile. Like,
There's a cleaning fee. Like,
yeah, no, yeah, that's my main thing. Is like, bro, it ain't even cleaning at that point. We getting a whole new seat installed.
Yeah.
Like,
So did your parents name you anything like after him?
See you at home.
No, I don't
No?
think so. I don't know what his name was. They just gave me a Southern name.
his name was Bobby.
Bobby.
Might have been a Robert. I don't know.
Yeah.
sorry, I got my name because my parents took one.
Right.
Yeah.
Go in the fridge or come home because they're full of fruit flies.
Yeah.
Probably
Well,
come home.
I got my name is Scott because my parents picked the first letter of my grandfather's name because he had passed away.
I would put them in a.
I'm the only one out of 13 kids that has a Southern name.
Yeah. There were 13 kids in your family?
Yep. I have 9 brothers and 4 sisters.
Oh,
3
my
sisters.
God. Oh my God. I have 1 sister. So
I'll take my brothers over my sisters anytime.
really?
Yeah. My sisters were kind of mean to me because I was really small.
Oh, well, yeah, okay, I can see that. Your brothers looked out for you, I bet.
Yeah, they did.
Yeah. Okay, here we go. Ionospheric layers, critical angle, frequency, HF scatter, NVIS. So we are on page 55. This one actually has page numbers. Where do the ionospheric layers reach maximum height? And that is directly underneath the sun. So if the sun is overhead, that's where the maximum layer height is built. The F2 region is responsible for longest distance radio waves because it's the highest one up. You can get about 2,500 miles on a skip. The E region, if it is active because it's lower, is good for about 1,200 miles. The D layer is responsible for absorbing signals. So if we look at our frequencies and our band plan, we will see that the lower frequencies down here up to about 40 meters, the D region is responsible for absorbing everything up to about 40 meters during the day. So 160, 80, 60, and 40 meters.
I'm busy.
Okay, let's see. So the D layer is responsible for absorption. Critical angle is the highest takeoff angle that returns a radio wave to Earth. So if you are too steep, it won't work. It'll just shoot on through. So scatter, we covered a little bit. When you send a signal off into the atmosphere, most of it will bounce if it gets to that point, but some of it will actually scatter backwards. And that allows people in the skip zone, which would normally be kind of a dead zone, to hear a little bit of you. And because of that, they're typically very weak. HF scatter kind of sounds like this, going up and down, and up, because it's weak in the first place, and it's not a reliable path. NVIS, again, is near vertical incident sky wave. Signals going almost straight up and straight down. Used for very local HF coverage. Okay, a notch filter. A notch filter is basically something that is drawn like this. Make sure I can do it. That's a notch filter. By tuning the notch, if there's an annoying signal right here, you can basically eliminate it using the notch filter. Notch filters are great for that. IF shift. Well, IF is intermediate frequency, and the way that a lot of receivers are built, they have multiple different frequencies where filtering is done internally. So an IF is an intermediate frequency where a frequency coming off your antenna is moved somewhere, then filtering is done, and then it's moved somewhere else using another mixer, and more filtering is done. IF shift allows you to change slightly the position of that filter. So you can eliminate interference by really nearby signals by moving the filter in the IF. This IF shift control does exactly that. An attenuator is measured in decibels. It basically is intentionally induced loss. So you might find a need to put in a 10 dB attenuator, which will knock down all signals by 10 dB or 10 times. If there's a really strong signal nearby, you can knock it down, which means that you stand a chance of being able to still use your receiver to listen to what you want to listen to. A noise blanker, if you hear a signal coming in that sounds like engine noise, that's a periodic noise. It's a pulse noise. A noise blanker listens to noise pulses, figures out what the frequency is, and when it happens, it reduces the receiver gain, thereby allowing you to make it sound like it's not there. Noise reduction control is very often it can be analog, it can also be a digital filter, and it attempts to figure out what part of the signal that you're listening to is noise and what part is real. Sometimes they do a good job, sometimes they don't. If they don't do a good job, your received signal can get distorted and it sounds kind of weird. An electronic keyer allows you to send dits and DAWs. Notice they say dots and dashes. They sound like this. Everybody hear that?
Mm-hmm.
Okay, so I'm using a straight key to do that. An electronic keyer would be something that if I threw the paddle one way, it would do this. If I went the other way, it would do this. By doing that, an electronic keyer allows me to send a lot faster than I can do a straight key. Using reverse or opposite sideband when you're listening to Morse code, it allows you to flip and listen to Morse code on the other sideband, which means that if there's interference on the upper sideband, Morse code is just one tone. It's one place on the band. You could flip to the other side where that annoying signal is not there, still copy your code, because it doesn't matter if you listen to code in upper or lower sideband, because it doesn't have a sideband, and be able to copy it through the noise. Split mode, we did a little yesterday. Split is different transmit and receive frequencies. It's very similar to RIT, which is receiver incremental tuning. Two separate VFOs or a dual VFO allows you to listen to two different frequencies. Okay, ALC, this is automatic level control. ALC basically gets into the transmitter circuit, and if you're putting out too much power, it allows you to change that and not overdrive your transmitter. So improper ALC causes distortion and can make you have spurious emissions, which basically cause splatter on your transmitted signal. And everyone who's listening will either not listen to you or get really mad at you. Symptom of transmitted RF being picked up by an audio cable. Well, the Vox circuit doesn't unkey the transmitter. The transmitted signal gets distorted, or you can have connection timeouts if you're listening to digital. A vacuum tube power amp. Okay, this is something that, this is amplifiers, because we are now using HF amplifiers. Load or coupling control of a vacuum tube amp. Okay. Dip the plate, peak the load. If you just remember that, dip the plate, peak the load. Dip the plate, peak the load. Dip the plate, peak the load. Dip the plate, that's basically changing the plate current from minimum plate current. Peak the load means that you're matching your load circuit to for maximum power output. If you have a vacuum tube amplifier, you'll have a plate and a load control. Dip the plate. So notice the plate current meter. You dip the plate, and then with regard to the load, maximum power output. You peak the load. For those of us who have had a vacuum tube amplifier or transmitter, this is your mantra. Dip the plate, peak the load. Dip the plate, peak the load. The reason to use ALC with an RF power amp is you can overdrive a power amp. If you overdrive the amplifier, it's not linear anymore, and you cause distortion. You can actually, in a solid state amplifier, you can drive it too hard and actually burn up your transistors. Solid state means transistors, by the way. Transmitter keying circuit. Well, in an amplifier, you have a receiver and a transmitter. On receive, you allow the signal to go right back down through to your radio. On transmit, you want to transmit. So there's a transmit receive switch. Often there's a little bit of a delay so that you can actually get back to listening, and then when you key the radio, you're in transmit. You allow all the circuits to switch. The device used to match transmitter output to an impedance is known as, once again, an antenna tuner. Like I said, there's actually quite a bit of overlap here. Okay, test equipment. Digital voltmeter has better precision than an analog meter. An analog meter just basically has a needle. Digital will say 4.9 volts. High input impedance, the higher the input impedance, the less impact it has on the circuit that you're measuring. So the best way to observe something is by not modifying it with your test equipment. So high input impedance keeps you from doing that. Analog readout can be preferred if you're dipping the plate and peaking the load, and dipping the plate and peaking the load. Notice the answer is when adjusting tuned circuits. Tuned circuits, the plate and the load, those are tuned circuits. By adjusting your knobs, that's what you're doing, and it's really nice. You don't really care if it's 180 milliamps or something. You just want to see that it goes down to a minimum. Test equipment that has horizontal and vertical amplifiers is called an oscilloscope. It puts a picture of a waveform on a screen. When checking the keying waveform of a Morse code transmitter, you want to look at it on an oscilloscope. Again, you want to see what the wave looks like. You can sample it by using an attenuated probe and then feed that into your oscilloscope and make a nice picture on the screen. An antenna analyzer needs to have your antenna and feed line. The nice part of an antenna analyzer, again, is that it can sweep a wide range of frequencies. And it could even go on frequencies that, again, are not even ham frequencies because it's not a legal transmitter. when making measurements, an antenna analyzer is sending out a pulse of energy at a frequency and looking for a signal coming back. Let's say that there's another transmitter nearby that's already transmitting and it's measuring signals coming back. It can confuse the heck out of your analyzer because there's signal coming back that it didn't put there. A directional watt meter can be used to measure standing wave ratio, or SWR. If you want to look and see what's coming out, you use a field strength meter. You can carry it around in your shack or go outside and look to see where your antenna's field strength is highest. What can you do with it? You can figure out a radiation pattern. You say, okay, I'm up here, I'm in front. Obviously, my pattern is strongest here. A two-tone test analyzer. By sending two different tones into a transmitter, you can see whether or not they are mixing internally. Ideally, they should not mix. They're two non-harmonically related audio signals. You put them in, you see if you get sum and difference or any other things that shouldn't be there coming out. Okay, interference. You know, this is basically almost the same as what we did yesterday. So we're going to come back to that if there's time. Resonant ground connection, networking, speech processors, S meters. Okay, we'll come back to that. We're going to go to the stuff that you really can't learn otherwise. Band edges, band segments we covered yesterday, where to be, where to not be. Heavy gauge wire, we covered that. Operating bandwidth is limited. We covered that.
Scott?
Yes.
I've got a question since we're talking about antenna analyzers.
Yes.
I've studied with myself about whether it's worthwhile for me to get an antenna analyzer.
Yes, it is. If you're ever gonna build anything or ever gonna put anything, the answer is yes.
So right after I got my license a little over a year ago, a friend of mine who is a ham said I needed to get a nano VNA. So I did. I gave about $80 for it at the time, but
a little
I've
harder
never
to
cared
use.
for it. And
Yeah.
I just don't feel that it's giving me information that I can use.
It has to be interpreted to use it, you know?
Yeah.
So that's the whole thing with the nano VNA. A nano VNA is an incredibly powerful tool, but you have to know how to use it. I mean, it provides way more information than anybody can use. If you want a simple, you know, like I have a nano VNA, but I also have my antenna analyzer. And for testing antennas, I go back to the analyzer because it's really easy to use.
Well, that's the impression I got.
Yeah, that's what I would do. Personally, that's what I would do. Okay. All right. Well, let's see. You know what? We're just going to cover this because we're getting there and we're doing a good job. Okay. If you have interference from a nearby transmitter, you can have distorted sound. This is typically on an old school telephone. If there's a nearby CW transmitter, you can hear humming and clicking. I used to get into my parents' stereo system and the telephone when it was a wired telephone. In order to eliminate RF interference, you might use a bypass capacitor. You could use an inductor. You could actually wrap something with a ferrite choke. So ferrite chokes are great for common mode interference. How can a ground loop be avoided? Well, as we have said, if you have a piece of wire, any piece of wire can function as an antenna. So if you have a piece of wire that's in the shape of a loop, you could actually have current running around and around and around inside the loop, transmitting signals. That's called a ground loop. How do you avoid that? You don't make loops. You just connect to a single point like a star network. If you have hum on your station's transmitted signal, you might have a ground loop. If you have a resonant ground connection, remember I drew that picture of a wire that has wavelengths on it because the wire is too long. You can have high voltages, high RF voltages on station enclosures and get a little shock from it. And what happens? The ground wire has high impedance on that frequency. In other words, ground is not ground anymore. Why should you use metal enclosures, and why then ground them? Well, if you are going to ground everything, then if there's 120 volts, if there's something that fails, then you probably won't get 120 volts on the case. Also, you want to bond all your equipment together. If you find that there's a large amount of interference, power poles with a failing transmitter can be really good for this. You have an arc. When an arc occurs, it's basically a very, very short duration pulse. Short duration pulses actually, by spectral analysis, it turns out, make noise at every frequency in the entire radio spectrum and beyond. So that's why lightning makes a crackling sound. And it doesn't matter what frequency you're tuned to. Lightning, if you're listening to a radio, will make a crackle. And it, again, doesn't matter what frequency you're listening to. So arcing will cause a wide range of static. A DSP, digital signal processing, as opposed to a fixed filter, is great because it allows you to do sampling and using the mathematics in the filter. Use time, basically sampling and then delay things, and that basically allows you to create a filter digitally, which means you change the math, you can change the filter. You can change the frequency response, you can change the bandwidth, you can change the you can change how steep the skirts are and stuff like that. Okay, speech processor. A speech processor is sort of like, if anybody remembers Dolby Sound, Dolby Sound was a way to sort of like boost different frequencies so your voice had more punch. That's what a speech processor does. Increases the intelligibility during poor conditions. Now, if you're using a speech processor and the conditions aren't poor and you're talking to somebody, they'll say, hey, you sound kind of peaky and weird. In which case, oh, you don't need the processor on. A speech processor increases average power from your voice. So, incorrectly adjusted, again, distorted speech, splatter, and excessive background pickup, because your microphone is essentially picking up more stuff and amplifying it. An S meter is right on the front panel of a radio. It measures received signal strength. One S unit, S units are measured from S0 to S9. One S unit is 4 times. And 4 times is how many decibels? 4 times is 2 times 2.
6.
That would be 3 plus 3 is 6 dB. So how does a signal that reads 20 dB over 9 compare to one that reads S9? 20 decibels is 10 plus 10 decibels, which is 10 times 10, which is 100 times the signal strength. We covered this one. Why should you never get too close to a band edge? If you're using sideband, you need to be at least 3 kilohertz away. Always use heavy gauge wire when doing mobile installations. The power socket, the cigarette lighter, is probably not designed to handle 22 amps, so don't use it for that. Things that can cause noise in a car: the battery charging system, the fuel delivery system, or the control computer. The spark plugs themselves are often really good for that too. You know, the ignition system makes very, very loud noise.
Yeah, windshield wipers too.
They can. Yeah, they can. The motors. Which of the following most limits an HF mobile installation? That would be the antenna system. What if you're trying to operate 80 meters? How long would an 80 meter quarter wave antenna be, roughly? So 80 meters, a quarter of that would be 20 meters. So how long is 20 meters?
That's 66 feet.
66 feet. Good luck putting that on your car. So what you can do is you can coil up the base You know, you can put a big loading coil at the base, which unfortunately makes your efficiency really low. You could put a coil up at the top, and because your maximum current is down at the base, that actually works better. Another way to do it would be to put something called a capacitance hat up top. So if I have a capacitance hat up top, it looks like that. Now, unfortunately, this adds a lot of extra weight to your antenna at the top, doesn't it? Especially if you're driving down the road at 60 miles an hour or 70 or 80 miles an hour, as the case may be. This is going to put a lot of force on it. So maybe now you have to use ropes to make sure it doesn't fall over. And so, as you can imagine, HF antennas, especially for the low bands, are quite the challenge. However, there are antennas that work better than others. You put your capacitance hat up top. There's a capacitance hat to lengthen a physically short antenna. You can put your coil up at the top. If you have a big open coil, that is the antenna known as a Texas bug catcher. You can figure out why. The purpose of a corona ball, if you get high voltage at the tip of the antenna, it's a ball and it allows it to discharge when you're transmitting. Sunlight is converted into electricity through photovoltaics. We call it a photovoltaic panel. The open circuit voltage from a silicon photovoltaic cell is about 0.5 volt. If you put a bunch of them in series, you can get a lot more voltage than that. You take a bunch of those and put them in parallel, you can get a lot of current out of it and charge up your battery. The reason that we use a diode between a solar panel and a battery is because a diode is a one-way device. So when the sun goes in behind the clouds, your solar panel voltage goes down. You don't want to backfeed the solar panel with your battery. So you use a diode to keep that from happening. The disadvantage of wind is that you have to figure out some way to store the wind energy, which is very difficult unless you have a lot of batteries. Which mode of voice communication is, okay, so we're on 70 now. Which mode of voice communication is most commonly used on HF? Single sideband. The nice thing about single sideband is that only one sideband is transmitted and the other one and the carrier are suppressed. Benefit? Less bandwidth, greater power efficiency. So if we look at our frequency charts, we will see that we have all these frequencies that are on HF. The breakover point is the 30-meter band. And notice you can't even use anything but CW or data or teletype on the 30-meter band, and you have a maximum power output of 200 watts. This is the break point. On the lower frequencies, you use lower sideband. Anything above that, you use upper sideband. So on 14 megahertz, you would use upper sideband. On 17 meters, which is 18 megahertz, 12 meters, which is 24 megahertz, you use upper sideband. Which is most commonly used for SSB in VHF and UHF? Again, by convention, upper sideband. If we're down on these bands, they are below 30 meters. So we're looking at 40, 80, 160. And we will be using lower sideband. And in fact, there it is, lower sideband. Now, this is not a requirement. This actually comes from the day when radios were were typically built by individuals. It was easier below that frequency to generate lower sideband. Today, it doesn't really matter. It's just good practice. If you show up on upper sideband, it might sound a little weird. You might not find anyone to talk to, but no one's going to get mad at you for doing it. So if you call CQ DX, DX is distance. If you're in the United States, you're looking for anyone outside the lower 48. If you want to break into a phone contact, you just announce your call sign. Just give your call sign. This is the same as on VHF and UHF. If someone's having a conversation on a repeater,
I love when you look healthy and youthful.
if somebody says this is N7JI, somebody will allow you to break in. ALC, what control is typically adjusted for proper ALC setting? That's automatic level control, which is a transmit function. So you change your transmit audio or your mic gain, which will allow your ALC to not clip your signal too much. Vox, I hate Vox personally. Vox is great for hands-free operation. However, if you're driving down the road and you're on Vox and somebody cuts you off and you release a whole bunch of expletives about that person's driving skills, that just went out on the air. So I avoid this by, or let's say you're sitting in your station and you're just tuning around and your kid comes and brings you a nice cup of hot coffee or hot soup and spills it all over your lap, right? If you have Vox turned on, the expletives that you scream will be transmitted over the airwaves, which is not a good thing. So that's what Vox is. Okay, CQ. Before you call CQ, what do you do on voice? Is the frequency in use, right? QRL means is the frequency in use. In Morse code, we use Q signals because they're a lot shorter. Let's see. Good amateur practice when choosing a frequency. Follow the voluntary band plan. Don't suddenly start showing up in the CW band using voice. People will look at you funny, and you'll possibly get a little notice that says, "Hey, don't do that." The voluntary band plan within the lower 48 says that between 50.1 and 50.125, if we look at our frequency chart, we will see on the 6-meter band 50.1 to 50.110. Notice that says DX window. That means don't go there. That is the DX window. It's only allowed for long distance contacts by agreement. When selecting a single sideband's frequency, you should be about 3 kilohertz away from the next station. And why is that?
Bleed over.
Bleed over, yep. You don't want part of your signal to be interfering with them. When you're in Morse code, your signal's about 150 hertz wide. 500 hertz is good spacing. During a contact, if you notice interference from another station, don't yell at them, "Hey, get the bleep, bleep, bleep off this frequency. I was here first." Say, "Hey, you know, the band seems to be changing. I'm now hearing you. Can one of us move?" No amateur station, except during emergencies, has priority access to any frequency. Even if you've been running a net there for every day at 6 p.m. for the last 40 years, that is not your frequency. If somebody else was there first, they're there first. When are you allowed to use any means at your disposal during an actual emergency? What frequency should you use to send a distress call? Anyone where anyone's going to hear you. And if you hear somebody doing that, you acknowledge the station and say, "Okay, what help do you need?" And okay, so who can operate as part of RACES? If you have an FCC issued license, you can be a part of RACES. Okay, now we're into Morse code. When establishing a CW contact, what speed do you send, right? If I can only copy this fast, and I send a CD, but I can send like this, but I can only copy at the slow speed, I should only send at the slow speed because people who are hearing me will send answers at the same speed that I sent. When you answer, you should send at the same speed that you heard, but not faster than you can copy. So you basically want to match to the lowest common denominator. 0 beat means that if this is the tone that you're receiving, that's also the tone that you're going to be transmitting on. It ensures that both stations are on the exact same frequency. That's called 0 beat. A C added to a Morse code signal to an RST. RST is readability, signal, and tone. If you add a C, that means that you have a chirp, which sounds like this, and is usually evidence of an unstable power supply. If a station sends QRS, that means send slower. QRQ, which is rarely heard, means send quicker. QSL means I got it, confirm. QRN is natural noise, which is static, as opposed to QRM, which is man-made noise, which is interference. QRV means I'm active and ready to receive or send messages. And these are just things that you got to memorize. Okay? So if I'm sending something on CW and I send K, K means anybody please answer. KN means only the station that I called, please answer. A pro sign. Pro signs are procedural signs that are used. And they are letters that are mushed together into a new symbol. For instance, SK, KN, AR. Those are letters that are then squished together. AR means I'm finished with a message. Message over. And I'm sorry you guys have to learn this Morse code stuff, but that's part of the test. Full break-in telegraphy, which is QSK, means that your receiver actually turns back on in between dits and DAs. So when you're sending, in between your dits and DAs, you can actually hear other stations break again. Okay, volunteer monitoring. The volunteer monitoring program is basically the non-legal FCC light program, if you want to think of it that way. It's run by the ARRL, and because we are typically a self-policing organization, we basically pay almost no money to use these bands, and the FCC therefore does not want to spend any money on our enforcement, so we enforce it ourselves. So amateur volunteers are formally enlisted to monitor the airwaves for rules violations so that the FCC doesn't have to get involved. It's a lot better to receive a note from a volunteer than to receive a note of violation from the FCC. To encourage amateur radio operators to self-regulate and comply. Volunteer monitoring program, they're really good at using direction finding skills to locate stations who are violating the rules. An azimuthal projection map. Okay, we were looking at this yesterday afterwards a little bit. This gives you distance and heading from one point on Earth to any other point. It basically folds the globe out into a flat disk. So, for instance, to go from the west coast to, let's say, Madagascar, which is up here in the upper right, we would have a beam heading of about 25 degrees, and it's a distance of about 10,000 miles. So that would be an azimuthal projection. True bearings and distances from a location. So how do you get there using the long path? Well, that which we showed was the short path. This, if you can get there up to 20 degrees, right there, using the long path, using the short path, the other way to go would be point completely the opposite and go the other way. So you'd actually point southwest and the signal would come back around the other side. So 180 degrees off from the short path. During the summer on the lower HF frequencies, for instance, what did I do with it? There we there. On the lower frequencies, 80 meters in particular, at night we have a lot of thunderstorms. Thunderstorms, lightning makes static. Static makes energy at all radio frequencies. Well, it turns out if you listen at night to 80 meters, you'll hear crash, 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 crackle, crackle, crackle. So you get lots and lots of static during the summer, especially on the low frequency bands. Okay, how do you determine if a frequency is clear? And you're looking for any contact with any station, say CQ, 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 this is and you give your call sign, N7JI, and you wait. And if no one answers, you do it again. The NATO phonetic alphabet: Alpha, Bravo, Charlie, Delta, Echo, Foxtrot, Golf, Hotel. The more you operate, the more you'll get used to these. When participating in a contest, you still have to identify your station per normal regulations, even if you're going super, super fast. How often do you have to identify your station? Every
10 minutes.
10 minutes.
10 minutes and at the end. Yep. Even if you're going super fast and making 8 contacts a minute, you still have to do it. You still have to follow the same rules. Okay. QRP
Wait,
is.
wait a minute. If
Yep.
you're in a contest and you're banging off every 8 contacts a minute, aren't you identifying every time you make that contact?
Not necessarily. What if I said N7JI contest and I get somebody answers, they give me their call sign and say, here's your call sign, 3A, Roger, and somebody else calls me immediately because they were waiting. I may or I may not. You know, they already know my call sign. If I'm giving my call sign, that slows me down. If they already know what it is, I don't need to tell them. So maybe you do it once a minute.
If you got that many backed up, then you need to make sure you throw in one every
once a
10
minute,
minutes,
once every 2 minutes,
5
something like that. Yeah.
Okay, I've not done enough contesting to know how intense it can get. Thank
Yeah.
you.
Well, actually, and if you're a de-expedition station, that does happen. You'll have 100 stations calling you at the same time.
Oh yeah, if you're out in some weird island where
Yeah.
nobody gets to you. Okay, that makes perfect sense. Thank you.
Yep. Okay, QRP means low power transmitting. Typically, by convention, QRP is 5 watts. Why do we keep a log? To help the FCC in case they look for info. Okie doke, here we go. Now, this is looking at the frequency bands. This is the one place where it is really different from the technician exam. We have all these different frequency bands that we basically have to know. Now, for the exam, you're not going to need to know all of them. But for when you're on the air, it is really good to have one of these charts nearby if you're trying to figure out where you are and where you're supposed to be. What segment of the 20 meter band is digital? 14070 to 112. Where do you find PSK 31? Below RTTY at 14070. And actually it turns out that FT8 is at 14074, is a lot busier than PSK 31. I suspect that the new question pool is going to have a lot of questions about FT8. What segment of the 80 meter band is most commonly used for digital? If we look at the 80 meter band, we will see way down here, and notice this auto digital, 3585 to 3.6, 3585 to 3.6, right there on the chart.
Is that an exclusive use allocation?
No.
Okay.
Well, here's another question. On what parts of these bands can you use Morse code?
I thought it was on all of them.
Everywhere. Yeah. Even though it says the red stuff is CW RTTY data, and like the yellow says extra voice CW and image and stuff like that, it's important to remember that you can actually operate Morse code on anywhere on any band where it's legal to be.
Okay.
The most common frequency shift for RTTY, again, that stands for radio teletype, that's been used for a really long time, is 170 hertz. And again, those signals that we transmit using RTTY have a name. They have 2 names, and they are called mark and space. Those are the 2 names of those signals, mark and space. And the shift is usually 170 hertz. When sending RTTY signals, we usually use lower sideband, although that's not a guarantee, but that's most common. When we use any other modes, JT65, JT9, FT8, we usually use upper sideband. As it turns out now, most people, in reality, when they're doing RTTY, they also use upper sideband. But by convention, it's usually lower sideband. For a serial data port, believe it or not, it's not a DB9. This is not a typo. It's a DE9. That's a 9-pin serial connector. And they're not all that common anymore. I suspect that question will probably go away on the new question pool too. When using FT8, you send call signs, grid locators, we did locators yesterday, and a signal report. And it's usually measured in decibels. FT8 is really an academic mode that allows you to just send information very, very briefly from one station to another. Importance on FT8, because everything is time synchronized, your computer time has to be accurate to within about 1 second. If it's not, you're going to have a lot of trouble talking to anyone. Why would you not be able to hear somebody on RTTY? You got mark and space backwards, you're on the wrong baud rate, or you're on the wrong sideband. All those things can and do happen. WinLink, if you're into emergency communications, WinLink is a hybridization between radio communications and the internet for message transfer. Very, very popular now. If you're trying to connect to a digital gateway station, you transmit a connect message on the published frequency. A PACTOR modem can be used to determine if the channel's in use by monitoring without making a connection. And if a PACTOR or Winmore station gets frequent retries, long pauses, or doesn't establish a connection, that means potentially that the frequency is really busy. This is actually peer-to-peer. PACTOR is one station to one station. Unlike Morse code, unlike voice, where you could chime in on a PACTOR or Winmore signal, you can't join an existing conversation. Okay, I think we covered this safety already. Routine evaluation, they have to do that, so I think we can just jump past it. Oh, here's one. When you're repairing an antenna, disconnect the feed line so you don't accidentally have somebody go down to the station and transmit into your hand. That would ruin your day. If you have a ground-mounted antenna, that means your feed point is at ground level. Some people put it inside a fence. Some people put a hedgerow around it so you can't get in. If you're using a climbing belt or a harness, make sure that you're not overweight for the device you're using. If you're climbing a tower, make sure that the power supply to the tower is locked out and tagged so that nobody raises it or lowers it. Nobody is able to put power on the tower that you're climbing. Why should you not use soldered joints with a lightning rod? Because the solder will instantly melt and then you won't have a connection anymore. Okay, safety. Use National Electrical Code, NEC. For 20 amps. 20 amps requires number 12 wire. 15 amps requires number 14 wire. Those are part of the National Electric Code. That determines what size wires you use in your house. Okay, if you have a 4-conductor connection, you have a 240 volt single phase source. 2 wires carry voltage. Where are you going to put your fuses or breakers? On the 2 wires carrying voltage. So you have 2 hot wires, a neutral, and a ground. A GFCI is a ground fault circuit interrupter that if there is a flow of current to ground, it will open it up and thus keep you from getting electrocuted by the hairdryer that you dropped into your bathtub. When connecting your house to an emergency generator, disconnect it from the outside world so you don't accidentally kill emergency workers. If you're going to use a generator, don't use it inside. Stick it outside. Don't put it anywhere near the intake of air into the house. You could die of carbon monoxide poisoning, which will ruin your day. Tin lead solder. If you eat after touching tin lead solder, you are ingesting lead. Bad idea. Okay, commission rules. I think this is getting to the very end. Yep. Okay, commission rules. Okay. Here we go. Okay, on which of the bands is a general class license holder granted all amateur frequency privileges, you can look at these and see 2200, 630, 160, 30, 12, 17. This is just a case of, oh, and 10 meters. This is just a case of going through and memorizing and knowing where it is. General class portion of the 80 meter band. Again, this is where you're just going to go grab your frequency chart and know where you're allowed to operate because the color of the chart says so. Let's see. So we'll kind of gloss past those because that's just memorization. Repeater use. Repeaters are allowed on 29.5 to 29.7 megahertz only. Repeaters are FM. They take up a lot of space. There is no phone allowed on 30 meters. There is no image allowed on 30 meters. It's just basically digital and data. Specific channels, 60 meters is an oddball band. Notice it has 1, 2, 3, 4, 5 channels on it. And that is hopefully someday going to change, but as yet has not. And notice we are a secondary user. So, as a secondary user, we cannot interfere with primary users. If a primary user is there, we need to move or stop. Frequency allocations, we are in region 2 of the ITU, that's North and South America. If you go to a different area, let's say you go to Guam or American Samoa, those are in a different region and the rules on frequencies are a little bit different. You have to pay attention. If you go to, even though you're using your US call, you're in a different area of the world. Any tower 200 feet or above has to be registered with the FAA. And you need to have lights on it, and it costs a lot of money. So don't do that. Local and state governments are permitted to regulate antenna radio structures. There has to be a reason. They have to permit it, but they can say no. Homeowners associations are really good at this. A beacon is for observation of propagation. The power limit for a beacon, this is just memorization, is 100 watts PEP. Does anyone remember what PEP stands for?
Peak envelope power.
Peak envelope power, yep. Okay. So there can only be one beacon from one location on one band. So you could have a location where you have 6 different beacons on 6 different bands. They just can't be on the same band. So there's a beacon band on the 10 meter band, which is 28.2 to 28.3. These are beacons that are set up all over the world. There are also beacons on all these different frequencies right here. And a worldwide system of propagation beacons by the NCDXF, Northern California DX Foundation, is set up from 18 different spots on Earth to transmit propagation beacons and allow people to listen to them and figure out where they're from. So it is recommended to stay away from those frequencies because when you transmit there, you're basically going to overwhelm them. We are allowed to retransmit weather and propagation forecast info. Some of our repeaters here do that in case of storms. We are allowed to transmit one-way communications, which are bulletins. We can also do for learning Morse code. So for instance, if I were sending code practice, I could send that out over the air for people to copy. Same rules here. We are not allowed to obscure the meaning of a message unless it is used for controlling a remote control station, remote control device like a car or an airplane, because we don't want somebody taking control of it and crashing it. So if you have a new protocol, you are allowed to use it so long as you are not the only one who knows it. So you have to publish it so other people can actually use it. They can decode it because you're not allowed to encrypt or obscure a meaning. And if you don't make a protocol public, then that is basically secret.
Does just obscuring the meaning mean using another language?
If it's a commonly known language, then no. But what if I came up with a code with you that said, when I say this word, here's what it means?
Well,
That would not be okay. It's not encryption, but I'm obscuring the meaning.
so if it's common knowledge, you can use it.
Correct. Good engineering and amateur practice. This is covered by part
When it
97.
says publicly disclose, are we talking about taking out an ad in the newspaper,
It could
filing
be
with FCC?
It could be putting it on your website. Just so
Okay.
long as people are able to find out what it is. Okay, so the next section, this is transmitter power and data emission standards. And I think we're right about at the end. There's VEs. And sorry, we're going to run a little bit over, but not by much. Everybody okay?
Yep.
We're good? Okay.
Yep.
Okay. Transmitter power. By and large, on the HF bands, on VHF bands, we're allowed to run 1,500 watts. Pretty much anywhere. 1,500 watts, 1,500 watts, 1,500 watts. The only places that we're not allowed to run 1,500 watts are on the 60 meter band. And if you're using an antenna other than a dipole, like I said, 60 meters is really weird. I've only been on it once. If you're using an antenna other than a dipole, you have to keep a record of the gain, because you're allowed ERP of 100 watts. ERP is effective radiated power. It's not radiated power, it's effective radiated power, so that has to take into account your antenna gain. The 30 meter band, right here, you're a maximum of 200 watts out. So that is one of those questions. 10.1 megahertz, that's in the 30 meter band, 200 watts. What measurement is specified by FCC rules for maximum power output? Peak envelope power. Okay, how much power should you use to carry out a conversation?
The least you need.
Least you need. Minimum power necessary to carry out the desired communications. And that is so that we don't overtax the resource. Other people can still use it. Maximum bandwidth on that weird 60 meter band, 2.8 kilohertz. Okay, here we go. Data rates. Okay, we are allowed to do data on HF. And remember that the more data you send, the faster you send it, the more bandwidth it takes. So below 28 megahertz, so that's everything except for 10 meters. So basically anything below 28 megahertz or 10 meters, so 12 meters, 15, 17, et cetera, we are allowed a screaming baud rate of 300 baud, which is really slow. On the 10 meter band, that bumps up because the band is bigger to 1200 baud. On 2 meters, we're allowed 19.6 kilobaud. So we're getting really fast here. By the way, a 19.6 KB modem, that was like 1992. And a 56K modem, that was like 1994. So on the bands higher up than that, which are this 1.25 meters and 70 centimeters, we're allowed 56 kilobaud. Above that, you get into the really high frequency bands. You can get into megabits, depending on the band you're on. You can actually get some really high data rates. Okay, being a volunteer examiner. Why do you need to know about being a volunteer examiner if you're taking a general class license?
You can actually start doing that.
Yes, you can. As a general class licensee, you can give technician class exams. You have to be 18 years old. You're only allowed to give technician licenses, and you have to be accredited by the volunteer examiner coordinator that you're working with. To give an exam, you need at least 3 accredited general class licenses or higher to give a technician exam. So can a general give a general class exam?
No.
Mm-mm. If you want to be a VE and give all exams, you get your extra class license. A certificate for successful completion of exam is good for 365 days. And if you do have a certificate and it says you have general class privileges. You passed your element 3 exam, which is the general exam, and you have a technician class license. You sign /AG or temporary AG. AG means amateur general. So you'd be, for instance, whatever your call sign is /AG until your license actually shows up as a general in the FCC database. If you're operating with your new privileges.
But that's pretty much quick, isn't it?
It's very quick now, but I will tell you that the FCC just had an outage of 3 weeks. If you were waiting for your upgrade and you had the piece of paper in hand, then you were operating /AG for 3 weeks because their system was not processing anything during that time. Okay, so if you ever held a general, advanced, or extra class license, all you need to do is take your technician exam and you get your general, advanced, or extra class privileges back if you can prove that you had it. So if it showed up in a database, you have an old copy of a license or something like that, or it was in the call book with your license class, then that will give you your old privileges back. If you have if your license has expired and the 2-year grace period has expired, you have to pass the element 2 exam, which is the technician license. And let's see. I think this is the last. Yep, this is the last section. Yay. Okay. Third party. The general class exam is a little, the general class is a little bit shorter. Besides, we covered a lot of stuff over the last 3 days. Third party. Well, third party, if it's permitted with another country, remarks of a personal character or messages related to emergency or disaster relief. The most common of which is, hey, let my relatives know that I'm alive. That's the most common one. Third party's amateur license has been revoked and not instated. If that person who was a third party had ever had a license and it was revoked, they can't become a third party. You can't carry traffic for them. Which of the following conditions require an amateur operator to take specific steps to avoid harmful interference? Well, if you're within a mile of an FCC monitoring station, or if you're secondary, or if you're using spread spectrum, we are actually allowed to do spread spectrum communications. If you're doing any of those things, you need to make sure that you are not causing harmful interference.
Now, spread spectrum is Wi-Fi, isn't it?
It's very similar to that.
So why would anybody want to transmit on that?
High data rates, good signal to noise ratio, and it's just an experimental thing. If you wanted to do spread spectrum, you could. Automatic digital control. We're allowed to do automatic digital control anywhere in 6 meter or shorter wavelength bands and in some HF bands. So these are kind of like the weird ones at the end, you know, that virtually nobody's ever going to do. So that's automatic digital control. What is required to conduct communications with a digital station operating under automatic control outside of the automatic band control segments? The station initiating the contact has to actually be controlled. In other words, it can't be automatic to automatic. In what part of the 13 centimeter band can you communicate with non-licensed Wi-Fi? Okay, that is the 2.4 gigahertz band. So we share frequencies, but we are not allowed to communicate with unlicensed Wi-Fi stations because they are not hams. As hams, we're allowed to communicate with other hams. Spread spectrum is limited to 10 watts. And under what circumstances are messages sent by digital modes exempt from Part 97 third-party rules? Does it matter if you're sending digital or voice or anything else? The rules are the rules. And that is the general class. So ask away, everybody.
What's the likely differences with the next batch of questions from these?
I think it's just, I mean, it's just basically modernization. You know, the high frequency bands, they don't change. The VHF bands, they don't change. The power levels don't change. It's really the fact that, you know, FT8 is the most commonly used mode on the air these days on HF.
Oh, yeah. Okay.
Stuff like that. I think there'll be more in the way of, you know, digital stuff. Electronics, it really doesn't change, you know. I mean, you think about it, a transistor's still a transistor, right?
That's what I'm telling myself not to be too worried about next month versus this month.
The questions are on hamstudy.org now. You can choose if you want to do general for June or general for July.
Oh, that's helpful.
When you're studying.
Sarah, do you have that open?
No, I can do it real fast though.
If you know how to get there, I'm going to, let me see, go to security. Okay. Now I just let everybody share the screen if they want to. So don't everybody do it at once, please. And I know this is a lot of material, but I hope it's been helpful and useful. And you know, this is also why I recommended that if you're taking this class, hopefully it's, you know, it's like being hit with a fire hose. So if you are in the middle of studying, you know, hopefully it makes sense. Hopefully it gets you through.
It's helped clarify so much.
Oh, good.
Yeah.
Okay. All right. Click on that 2023 to 2027. Oops.
I was able to answer a few more questions on the test as a result of the class. I still suck at the practice test, but at least I suck a little less than I did before.
What are you using to practice?
That's the one with, it's an app on my phone. I just put in ham study and it pops up.
Oh, no. Do you download something called Ham Radio Exam -General?
Ham Radio Prep?
Nope. Ham Radio Exam -General.
Ham Radio Exam. Okay.
Because otherwise it's not free. This one is free. And what's cool about it is that you can study one section at a time. It's about 15 questions at a time that from each section of the test. And it allows you to basically drill and drill and drill and drill on one section and get really good at it and then move on to the next one.
You can't do that. You can't do that on the study mode of ham study.
I don't know.
I think so. I think you can.
Can you actually practice it?
Yeah, that's how this ham radio prep is set up.
Yeah, I
I'm
did
doing
one of the
better
practice
on
tests
some
this morning.
sections than the others.
Okay.
Yeah, so ham study is the whole section, and then the app will break that section down into multiple parts. So usually 3 to 5 segments within each of these groups.
Okay.
Could I ask Scott for a repeat on that URL for ham radio exam?
It's actually just an app.
Okay, can you repeat that app again? It's ham radio.
Ham radio exam. Yeah, I'll put it in the chat.
Ham radio exam
-General. Here, I just put it in the chat.
Okay.
So so for those who's using Ham Radio Prep, how do you like it? I've heard of it. I've never used it.
I like it fine.
Ham radio exam.
Frustrating how dumb I am, but good.
There you go.
I like it, but I found that I do better on those tests than the one that you put up in the chat. Like I get higher grades in the ham radio prep test. I don't know what the difference is, but I definitely do better on their test than the one you have posted.
That doesn't make any sense. It's the same question.
I agree. I get 90s on their tests and I pass the one you put up at like low 80s, high 70s.
Huh.
I don't know why. I know they're the same questions. Maybe I don't know. That's the technician level, not the general level.
Yeah.
I don't do that good in the general level.
Well, if you've got, let's see, remind me to ask about adding HF to a hybrid Highlander. That's a good question because my wife has a hybrid Highlander, and my solution is really simple.
Yes.
She doesn't let me. It's her car.
My
Well,
wife's in the same.
This is my car.
Yeah, she won't let me because it's her car. I
So-
mean, HF Mobile is one of those things. I've done it. It takes a lot of work, but if you do it right, it works great.
Yeah, I'm feeling tempted to make a trailer with an NVIS antenna on it.
What band do you want to
and
operate?
just bypass all the complexity of putting an antenna on a hybrid.
What bands do you want to operate?
That's a very good question. Deserves an answer.
Like
Can
20
I have the
meters.
next question, please?
Well, so here's my old car. All right, this is when I had more time to do things like that. Here's my old car. Okay, so here's my old car. I had, and I still have, a bracket which is mounted from the underside of the car. And on this, I have a screwdriver antenna. So that is with the whip. So it's actually about this tall. With the whip, that goes up to about 13 feet. And
These are the old antennas the police cars head back home.
yeah. Well, and this, because it's a screwdriver antenna, essentially what it is a metal barrel, right, with beryllium copper finger stock around the inside. And then there's a screwdriver motor in the base, which is on a threaded shaft. And there's another part of this, which is a coil, which goes around and around and around and around and mounts to the top. And here's the top where the whip is. The screwdriver with the threaded shaft raises and lowers this coil. So if it's all the way retracted, you basically get no coil. If it's all the way extended, you get maximum coil, which changes your resonant frequency of your antenna. And because of that, on my console, so here's the seat, and on the console down here, I had an up and down switch. And so I could raise it and lower it from inside the car. I had the radio mounted here, right next to the console. And so I had a battery connection going to here. And I had my RF going down through here, down under here, outside to here. And then, because that only goes so far, I grounded the hood to the frame. I grounded the trunk lid to the frame. I grounded the exhaust pipe to the frame. I grounded my bracket to that same place. So I had bonding cables everywhere. And then on top of that, I also have, I'm going to do it in yellow here because I know you hate yellow, but I'm going to do it here. All these ignition system wires, right? Which made a terrible amount of racket. I replaced the ignition system wires with special noise suppressing ignition wires. They were this is almost 30 years ago. They were $100 a set for a four cylinder. But they eliminated the noise. And they lasted the life of the car. And this car, I made thousands of contacts all over the world from this car.
With the antenna extended to 13 feet while you're driving down the road.
Well, actually, the whip is 8 feet long. So it would go anywhere between, let's say 13, between like 10 and 13 feet, based on how much of the coil, the coil was extended. Oh, no, it had nothing to do with that. I mean, there was no issue with wind resistance at all. I mean, I built this thing. I overbuilt this so much. This bracket was mounted to the frame of the car. I mean, there was nothing that was going to knock this down. It might vibrate a little, but that's it. The whip was fine.
I did have the privilege of building my own antenna.
Yeah.
With the help of the group that I belong to.
Mm-hmm.
We just bought all the supplies and they were there right with us so we could build our own. So it helped me a lot.
You learn a lot building stuff. I mean, I And I went to the point on this car. I mean, I worked on it for 2 months every day during the summer. I took the seats out. I took the carpet out. You know, on the roof, I put for VHF, UHF, I pulled down the headliner, drilled a hole in the roof for a really solid antenna. I repainted where I drilled the hole. I mean,
So did you put hydraulics in the back wheels too?
No, I did not. There was no need. But what was great about this? What was great about this install was literally I could drive down the road and I could work. You know, if I wanted to change bands, I just hit the up and down button, and I could change bands as I was driving. And because I had the rear defroster, I could see the defroster lines and know about where I was supposed to be.
That's actually pretty clutch.
It was really, it was really helpful.
That's actually a flex. I won't lie.
Yeah.
How long would it take to go from like the shortest length to the full 13 feet?
About 2 minutes.
That's not bad.
Yeah. The only problem is if I ever pulled into a drive-through, I couldn't go through.
Right. Too tall.
I'd have to get out and take the antenna off if I wanted to park in a parking garage or go get gas. Sometimes it would scrape the underside of the, the canopy. And I had and as I was driving, I had to look at, clearances.
Right. So as awesome as that is, to pause on that for a moment. So let's say we're walking into the technician exam tomorrow. What is the first few things you would write on your blank piece of paper?
You tell me.
Ohm's law.
Ohm's law. That's the big one.
In its with its various things, right?
Yep.
With E and then P and then Z. Do we need all three of them or just those two?
Just those two.
Okay.
And then the other one? The relationship between frequency and wavelength. That's it. Those three things. Those will basically do most of the math. And there's a good chance you won't have to do any math at all.
I sure hope not.
But I mean, at most, it's going to be 2 or 3 questions out of 35.
Right.
So
I'd actually rather do the math than to remember the micro, the pico, the guacamole, the whatever.
Yeah. Well, the only tricky thing is that there's, by the way the exam is generated, there has to be a certain number of questions from each section. There's a minimum and a maximum.
Right.
So you can't get an exam that's 22 math questions.
I wish I could, though.
Yeah.
I would take that.
And maybe you should then you're going to do great on the extra.
Yeah.
Because that's a lot of math.
One day.
Is it similar to the way we take the practice tests, like on the apps and stuff? It's just a randomly generated test?
It's exactly the same. It's identical.
Okay.
Okay. I'm going to go.
In fact, if you've used hamstudy.org, the same guy who wrote hamstudy.org wrote the examination tool. It looks exactly the same, except that it's real.
Well, and the thing I like about hamstudy.org is they do break it down at the end. They do break it down in the different sections of how well you did in one section versus another section.
Yep.
At the end. So.
Do you get a score or is it pass fail?
You get a score.
No, you get a score.
You get a score. Okay. You will know how you did.
Yeah.
You get an aptitude percentage, right?
Well, I mean, for the real exam, we just tell you what your score was.
I'm talking about the practice.
Oh, yeah. It tells you how you did on that section. So you can see
what do you call an amateur radio operator who gets a perfect score in his exam questions?
Ooh, I don't know.
Call him a ham.
Oh, good.
What do you call somebody who gets the bare minimum qualified.
You also
questions.
call him that. What do you
Bingo.
call what do you call the guy who graduated last in his medical school class?
Doctor.
Doctor, yeah. Okay, all right, I got one more. I heard this morning. Why did the skeleton cross the road? Anyone?
Got tired of waiting for the chicken to get there?
Nope. He had a bone to pick with the chicken.
He had a bone to pick with the chicken. Oh my God, that is awesomely horrible.
I know.
Do you know why the chicken crossed the road in Texas?
I don't.
To prove to the armadillo that it can be done.
Yeah.
Okay.
Okay.
We're on chicken jokes, so I'm gonna go plug in my phone and keep studying. Thank you, Scott, so very much. This helped huge. This is exactly what I needed. So,
good luck, everyone.
Yes.
Yes.
And I know for some it was maybe a little much. I mean, it's a lot of material, but you know, you guys have done a great job, and you've asked and answered lots of really hard questions, and I really appreciate it. You know, every class that I teach, the vibe is a little bit different. So this one was different than every other one I've done before.
Well, the math was a bit much for me, but at least you left me in a good mood because I like the antenna part and stuff.
Yeah.
Yeah. Well, and that's where I like it's recorded and I can go back and rewatch and watch it slower and rewatch certain parts if I need that to, you know, in my notes, I said, you know, possibly go back and rewatch and then go through the book again and stuff. So I appreciate having that.
Hey,
not